At the limits of our understanding lies a mystery older than time itself. Before galaxies, before stars, before even light, there was something. Not a place, not a moment, but a state of existence where the rules of reality didn't yet apply. Space didn't have shape. Time didn't move forward. It was a void so complete we can barely describe it. Yet from that nothing, something began. In the earliest fractions of a second, the universe expanded with unimaginable speed. Energy, matter, and space itself unfolded from a single point, or perhaps something stranger. In 1929, Edwin Hubble discovered that galaxies are moving away from us, proving that the universe is still expanding. But why did it start? What triggered the birth of everything? The idea of nothing is a profoundly complex and endlessly fascinating subject that has puzzled thinkers for millennia, from ancient philosophers to modern scientists. When we talk about nothing, especially in the context of the universe's beginning, or what might have existed before the Big Bang, it is crucial to understand that nothing is not a single simple concept. It carries different meanings in philosophy compared to science, and even within science itself, its definition shifts as our understanding of reality evolves. To truly grapple with the question of whether nothing existed before the Big Bang, we must first clarify what exactly we mean by that seemingly straightforward word. In philosophy, nothing often refers to absolute non-existence, a state utterly devoid of being of properties of anything whatsoever. This is the most profound and perhaps most challenging definition to grasp, because it is by its very nature the absence of all that we know. For ancient Greek philosophers like Aristotle, the concept of a true vacuum or empty space was problematic. He believed that nature abhorred a vacuum, arguing that every space must be filled by something, even if it was an invisible substance or an ether. His view was largely a reaction to earlier atomists, who proposed that the universe consisted of tiny, indivisible particles moving in an infinite void or empty space. For Aristotle, nothingness was more akin to a privation, or the absence of a particular quality or form from something that already existed, rather than a complete absence of existence. The idea of something arising from literally nothing was largely inconceivable in many classical philosophical systems, where creation was often seen as the rearrangement of pre-existing material, or an emanation from a divine source. Centuries later, the philosopher Gottfried Wilhelm Leibniz posed his famous question, why is there something rather than nothing? This query encapsulates the core philosophical challenge of existence itself. If absolute nothingness is the simplest and most natural state, then why do we find ourselves in a universe filled with matter, energy, space, and time? It implies that something must account for existence itself, not just the particular form it takes. From an existentialist perspective, nothingness can also refer to the absence of inherent meaning or purpose in the universe, forcing humanity to create its own values and significance. This philosophical exploration of nothingness often pushes the boundaries of human intuition, requiring us to think beyond our direct experiences of the world, where even what we perceive as empty is filled with air or fields or potentials. Moving from the abstract realms of philosophy to the concrete observations of science, the meaning of nothing begins to change fundamentally. For a long time, even in scientific discourse, empty space was considered relatively inert, a passive stage upon which the drama of the universe unfolded. The 17th century marked a pivotal shift with experiments by Torricelli, Pascal, and Boyle, providing experimental proof of the vacuum. Torricelli's barometer, for instance, demonstrated that mercury could be suspended in a tube by atmospheric pressure, leaving a space above the mercury where air was absent, a void. These experiments challenged the Aristotelian notion of a plenum, where all space must be filled, and laid the groundwork for understanding empty space as a physical entity capable of being studied. However, even then the vacuum was often seen as simply the absence of matter, a region where particles were not present. Later in the 19th century, the concept of the luminiferous ether was introduced, a hypothetical medium thought to permeate all of space to carry light waves. This was another attempt to fill the vacuum, reflecting a discomfort with the idea of truly empty space, until Einstein's theory of relativity showed the ether was unnecessary. The advent of quantum mechanics in the 20th century profoundly revolutionized the scientific understanding of nothing, or more accurately, the quantum vacuum. In the classical view, a vacuum is simply space with no particles in it. However, quantum mechanics teaches us that this is not true. According to the Heisenberg uncertainty principle, which states that certain pairs of physical properties like energy and time cannot both be known with perfect precision, simultaneously, even empty space is teeming with activity. It is impossible to have an absolutely empty void where nothing is happening. Instead, the quantum vacuum is a dynamic, bubbling soup of virtual particles, constantly popping into existence and then vanishing again in incredibly short periods of time. These virtual particles are not directly observable, but their effects can be measured. One of the most striking pieces of evidence for the quantum vacuum's activity is the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that if two uncharged metallic plates are placed very close together in a vacuum, they will experience a small but measurable attractive force. This force arises because there are fewer virtual particles and their associated electromagnetic fluctuations that can exist in the tiny gap between the plates compared to the space outside the plates. The difference in quantum vacuum energy between the inside and outside of the plates creates a net inward pressure pushing the plates together. The experimental verification of the Casimir effect demonstrates that the quantum vacuum is not inert, but possesses real measurable energy known as zero-point energy. This energy represents the lowest possible energy state of a quantum field even at absolute zero temperature. Furthermore, in modern quantum field theory, every fundamental particle in the universe is understood not as a distinct tiny ball, but as an excitation or vibration of an underlying quantum field that permeates all of space. For example, there is an electron field, a photon field, a quark field, and so on. The vacuum state in this context is the lowest energy state of all these quantum fields. It is a state where there are no excitations, no particles, but the fields themselves are still present and continually fluctuating. This means that even in the absence of observable particles, the fundamental building blocks of reality, the fields themselves are still very much there. The Higgs field, for instance, is a field that permeates all of space and interacts with certain fundamental particles, giving them mass. Even in the vacuum state, the Higgs field has a non-zero background value, known as its vacuum expectation value, which is crucial for the existence of mass in the universe. So the scientific vacuum is far from nothing in the philosophical sense. It is a complex energetic entity with inherent properties and potential. When we extend this understanding to cosmology and the question of what existed before the Big Bang, the definition of nothing becomes even more intricate. The standard Big Bang model describes the evolution of the universe from an extremely hot, dense state. It points to a beginning where all matter, energy, space and time were compressed into an infinitely small and infinitely dense point called a singularity. This singularity represents a breakdown of our current laws of physics. If space and time themselves began at the Big Bang, then the concept of before the Big Bang loses its conventional meaning. How can something exist before time began? Does nothing then mean the absence of space and time as we know them, a state that is fundamentally inconceivable within our normal experience? Many contemporary cosmological theories attempt to address this issue by proposing different scenarios for the pre-Big Bang epoch, or by seeking to avoid the singularity altogether. Some theories suggest that what we perceive as the Big Bang was not the ultimate beginning, but rather a transition from a previous state. For example, cyclic universe models propose that our universe is just one phase in an endless cycle of expansion and contraction, or bounces. In these models, nothing before our Big Bang is simply the highly compressed or collapsed state of a previous universe, or the phase between one cosmic cycle and the next. This means that something always existed in some form, just not necessarily the current form of our universe. Another influential idea comes from inflationary cosmology, which proposes a period of extremely rapid expansion in the very early universe. This theory introduces the concept of an inflaton field, which drove this rapid expansion. In some inflationary scenarios, the Big Bang itself could have arisen from a quantum fluctuation in a pre-existing quantum vacuum, or a false vacuum, a state of higher energy that rapidly decayed, releasing enormous amounts of energy and creating the matter and radiation we see today. In this view, nothing is not an absolute void, but a highly energetic and unstable quantum vacuum from which our universe inflated. This vacuum might itself be part of a larger meta-vacuum, giving rise to multiple universes in a multiverse scenario. In such a context, our universe springs from a quantum foam, or a larger cosmic substrate, which is far from nothing in the absolute sense, but rather a fertile ground for cosmic creation. The search for a theory of quantum gravity which aims to unify general relativity, the theory of gravity at large scales with quantum mechanics, the theory of matter at small scales is crucial for understanding the ultimate nature of nothing before the Big Bang. Theories like loop quantum gravity suggest that space-time itself might not be continuous, but rather composed of discrete fundamental loops, or quanta. In this framework, the Big Bang singularity could be resolved as a quantum bounce, where the universe did not collapse to infinite density, but instead reached a minimum size before rebounding into expansion. In this view, there was no true singularity, and thus no nothing, in the sense of complete non-existence before the bounce. Similarly, string theory, a candidate for a unified theory of everything, posits that fundamental particles are not point-like, but rather tiny vibrating strings. It also suggests the existence of extraspatial dimensions curled up or hidden from our perception. In some string theory-inspired cosmological models, the universe's beginning might be explained as a collision of higher dimensional branes, or membranes existing in a larger bulk. In this context, nothing before the Big Bang would be a state of other branes, or the higher dimensional space they inhabit a complex and energetic realm that predates our familiar four-dimensional space-time. These models hint at a pre-geometric state where space-time as we know it does not yet exist, but rather emerges from a more fundamental quantum foam or network. Ultimately, the scientific understanding of nothing, especially in the context of the universe's origin, is constantly evolving and becoming more nuanced. It is clear that the nothing from which the universe may have sprung is not an absolute philosophical void. Instead, it is understood as a highly complex dynamic and potentially energetic state that defies our everyday intuition. Whether it is a quantum vacuum teeming with virtual particles, a pre-existing space-time from a previous cosmic cycle, a higher dimensional brane, or a fundamental quantum foam, the scientific nothing is always something with inherent properties and the potential for existence. The distinction between philosophical nothingness and scientific nothingness is paramount. When scientists discuss the origin of the universe from nothing, they're almost always referring to a scientific vacuum, a state of minimum energy of quantum fields, or a realm where space and time as we understand them had not yet fully emerged. They are not typically referring to the absolute non-existence of everything, including the laws of physics themselves. The question of whether true absolute nothingness could ever spontaneously give rise to something remains largely in the domain of philosophy and metaphysics, as it lies beyond the empirical methods of science. Our attempts to define and comprehend nothing continue to push the boundaries of human thought, revealing that the apparent void is far richer and more complex than we could ever imagine. The quest to understand what, if anything, came before the Big Bang fundamentally depends on how we define that elusive concept of nothing itself. The Big Bang theory stands as the leading cosmological model explaining the observable universe's origins and evolution. It describes how the universe began from an extremely hot, dense state and has since expanded and cooled to become the vast, complex cosmos we see today. It is important to understand that the Big Bang was not an explosion in space, as if matter suddenly flew outward into pre-existing emptiness. Instead, it was an expansion of space itself, carrying matter and energy along with it. Every point in the universe expanded away from every other point, creating the fabric of space-time. This concept is fundamental to grasping the theory's core message that the universe has a history and that it has changed dramatically over time. The development of the Big Bang theory was a gradual process built on a series of key observations and theoretical insights over many decades. One of the earliest and most pivotal figures was Georges Lemaitre, a Belgian priest and physicist in the 1920s. Independently of others, he proposed that the universe began from a single primordial atom, a highly condensed state of matter and energy that expanded outwards. His idea later became a cornerstone of the Big Bang model, although the term Big Bang itself was famously coined much later by astronomer Fred Hoyle, a proponent of a rival theory the steady-state theory. Hoyle used the term disparagingly to describe Lemaitre's idea of a definite beginning for the universe, but it stuck and ironically became the widely accepted name. Another crucial piece of the puzzle came from Edwin Hubble, an American astronomer in the late 1920s. Hubble observed that distant galaxies were moving away from Earth and that the speed at which they receded was proportional to their distance from us. This relationship, known as Hubble's law, provided the first direct observational evidence for an expanding universe. The light from these distant galaxies was shifted towards the red end of the spectrum, a phenomenon called redshift, similar to how the pitch of a siren changes as an ambulance moves away. This redshift indicated that the space between galaxies was stretching, carrying the galaxies farther apart. Hubble's findings strongly supported Lemaitre's concept of an expanding universe and undermined the prevailing static universe models. For a time in the mid-20th century, the Big Bang theory competed with the steady-state theory. The steady-state model proposed that the universe was eternal, unchanging in its overall appearance even as it expanded because new matter was continuously being created to fill the gaps left by the expansion. This meant the universe had no beginning and no end. However, two major discoveries decisively tipped the scales in favour of the Big Bang model. The first was the discovery of the cosmic microwave background radiation, or CMB, in 1964 by Arno Penzias and Robert Wilson. They were working with a large horn antenna and detected a persistent faint static, like signal coming uniformly from all directions in the sky. This signal was initially thought to be interference, but it turned out to be the leftover radiation from the very early universe. According to the Big Bang theory, the early universe was extremely hot and dense, filled with a plasma of matter and radiation. As the universe expanded, it cooled and eventually became transparent, allowing this radiation to travel freely. The CMB is essentially the cooled-down afterglow of the Big Bang, a relic from a time when the universe was only about 380,000 years old. Its uniformity and temperature distribution precisely matched predictions made by the Big Bang model, providing incredibly strong evidence for a hot, dense beginning. The second major piece of evidence came from the observed abundance of light elements in the universe. The Big Bang theory predicts that in the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion reactions to occur, a process called Big Bang nucleosynthesis. During this period, protons and neutrons fused to form the nuclei of light elements, primarily hydrogen and helium, along with trace amounts of lithium. The theory accurately predicts the relative proportions of these light elements observed in the universe today, about 75% hydrogen and 25% helium by mass. This precise agreement between theoretical predictions and cosmological observations served as another powerful confirmation of the Big Bang model's accuracy. These three pillars, the expansion of the universe, the cosmic microwave background, and the abundance of light elements, form the robust observational foundation of the Big Bang theory. The story of the Big Bang begins at an incredibly early moment in time, perhaps as early as the Planck epoch, which is approximately 10 to the power of minus 43 seconds after the conceptual beginning. At this time, the universe was unimaginably hot and dense, so much so that all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, are thought to have been unified into a single superforce. Our current understanding of physics breaks down at this extreme point, and a complete theory of quantum gravity is needed to truly describe this earliest moment. Immediately following the Planck epoch, the universe entered a period of rapid and exponential expansion, known as the inflationary epoch. This concept was proposed in the early 1980s primarily by Alan Guth to address several puzzles that the standard Big Bang model on its own could not fully explain. These problems included the horizon problem, which questioned how distant parts of the universe could have the same temperature if there had not been enough time for light to travel between them to equalize their temperatures. The flatness problem pondered why the universe's geometry appears so incredibly flat, which is a very specific condition among many possibilities. And the monopole problem addressed why certain exotic heavy particles predicted by some theories are not observed today. Inflation suggests that the universe underwent an incredibly brief but mind-bogglingly rapid expansion, stretching its size by a factor of at least 10 to the power of 26 in a tiny fraction of a second. This superexpansion would have smoothed out any initial irregularities, flattened the universe's geometry, and diluted away any unwanted exotic particles, effectively solving these cosmological problems. Inflation also provides a mechanism for generating the tiny density fluctuations observed in the cosmic microwave background, which later grew through gravity to form the large-scale structures like galaxies and galaxy clusters we see today. After inflation, the universe continued to expand, but at a much slower rate. The extreme energy of the inflationary period was converted into a hot, dense soup of elementary particles and antiparticles, a state known as the quark-gluon plasma. At this point, the universe was still too hot for quarks to bind together. As the universe continued to cool, the strong nuclear force became strong enough for quarks to combine, forming protons and neutrons, which are types of hadrons. This period is known as the Hadron Epoch. Crucially, during this time, there was a tiny asymmetry between matter and antimatter. For every billion antiquarks, there were 1,000,001 quarks. As the universe cooled, matter and antimatter annihilated each other, leaving behind a small surplus of matter, which eventually formed everything we see today. Following the Hadron Epoch was the Lepton Epoch, where leptons such as electrons, positrons and neutrinos dominated the universe's energy density alongside photons. About a few minutes after the Big Bang, when the universe had cooled to about 1,000,000,000 degrees Celsius, the conditions were just right for Big Bang nucleosynthesis (DBN) to occur. Protons and neutrons fused together to form the nuclei of the lightest elements, deuterium, an isotope of hydrogen, helium-3 and helium-4, and trace amounts of lithium-7. These reactions lasted for only about 20 minutes, before the universe became too cool and too diffuse for fusion to continue. The precise ratios of these light elements observed in the universe today are one of the most compelling pieces of evidence for the Big Bang model. These abundances perfectly match the predictions made by the theory, providing a powerful confirmation of the universe's hot, dense early state. For the next several 100,000 years, the universe was a hot, opaque plasma, primarily composed of ionized hydrogen and helium nuclei and free electrons. Photons, light particles, were constantly scattering off these free electrons, meaning light could not travel far without being absorbed or deflected. This was the photon epoch where radiation dominated the universe. As the universe continued to expand and cool, the temperature eventually dropped to about 3,000 Kelvin, roughly 38,000 years after the Big Bang. At this critical temperature, electrons were able to combine with hydrogen and helium nuclei to form stable neutral atoms. This event is known as recombination. Once electrons were bound in atoms, photons were no longer constantly scattering off free charged particles. The universe became transparent and photons were free to travel across space unimpeded. These photons form the cosmic microwave background radiation, a direct observable relic of this epoch, often referred to as the surface of last scattering. It is literally the oldest light we can detect, providing a direct image of the early universe. After recombination, the universe entered a period known as the Cosmic Dark Ages. For hundreds of millions of years, there were no stars or galaxies to produce light. The universe was filled with neutral hydrogen and helium gas, and a diffuse background of CMB photons. This was a period of darkness and gradual evolution, as gravity slowly began to pull together the slightly denser regions of gas and dark matter that were seeded by the tiny fluctuations from the inflationary epoch. Over vast stretches of time, these gravitational pulls led to the collapse of gas clouds, forming the first stars and quasars. These first luminous objects began to reionize the neutral hydrogen gas, filling the universe with ultraviolet radiation. This marked the end of the Dark Ages and the dawn of the cosmic reionization era, roughly 150 million to 1 billion years after the Big Bang. As the universe continued to evolve, gravity played an increasingly dominant role in shaping its structure. The small density enhancements continued to grow, attracting more matter. This led to the formation of progressively larger structures. Galaxies formed from collapsing clouds of gas and dark matter, and then clustered together to form galaxy groups and larger galaxy clusters, which themselves are organized into vast superclusters. This hierarchical clustering process led to the creation of the cosmic web, a filamentary structure of galaxies separated by vast empty voids, that characterizes the large-scale distribution of matter in the universe today. Dark matter, an invisible and mysterious substance that interacts only through gravity, is crucial for this process. It provides the gravitational scaffolding around which ordinary matter collects. Without dark matter, the universe's structures would not have formed as they have. In the last few billion years, the expansion of the universe has taken an unexpected turn. Observations of distant supernovae in the late 1990s revealed that the expansion is not only continuing but is actually accelerating. This acceleration is attributed to a mysterious force or energy called dark energy. While dark matter helps structure formation, dark energy works against gravity, pushing things apart. It is thought to be a property of space itself, or a new kind of energy field. Dark energy now dominates the energy density of the universe, and its continued influence will determine the ultimate fate of the cosmos. If dark energy remains constant or increases, the universe will continue to expand at an accelerating rate, leading to a cold, empty future, where galaxies move so far apart that they become isolated and stars eventually die out. Despite its remarkable success in explaining a vast array of cosmological observations, the Big Bang theory still faces significant challenges and leaves several fundamental questions unanswered. The most prominent question remains what happened before the Big Bang itself. The theory describes the evolution of the universe from a very early hot, dense state, but it does not fully explain what initiated that state or what came before it. The singularity at the beginning, where our current laws of physics break down, remains a theoretical hurdle. The precise nature of dark matter and dark energy, which constitute the vast majority of the universe's mass and energy content, also remains unknown. While their effects are observed, their fundamental properties are still a mystery. Furthermore, the mechanisms and precise details of cosmic inflation are still areas of active research and debate. While inflation solves several problems, the exact field that drove it and how it transitioned to the hot Big Bang plasma are not yet fully understood. The realization that our universe is not a static, unchanging entity, but rather a dynamic system that is continuously expanding, is one of the most profound discoveries in the history of science. This understanding fundamentally reshaped our view of the cosmos, moving us away from ancient philosophical notions of an eternal and fixed universe towards a model of cosmic evolution with a definite beginning. The evidence for this expansion is abundant and compelling, primarily rooted in meticulous astronomical observations and the underlying physics of light and gravity. To fully appreciate how we know the universe expands, we must delve into the historical context, the observational methods and the theoretical implications of this remarkable phenomenon. Before the 20th century, the prevailing view of the universe was largely static. Isaac Newton's laws of gravity, for instance, suggested that a static universe would be inherently unstable, eventually collapsing under its own gravitational pull unless it was infinitely large and uniformly distributed. However, such an infinite universe presented its own set of paradoxes. When Albert Einstein developed his theory of general relativity in the early 20th century, which describes gravity as the curvature of space-time, his initial equations also pointed towards a dynamic universe, either expanding or contracting. Uncomfortable with a non-static universe because it conflicted with the then accepted view, Einstein introduced a mathematical term called the cosmological constant into his equations to force the universe to remain static. This term acted as a repulsive force counteracting gravity. This move later became one of his self-confessed biggest blunders in scientific thought. Intriguingly, around the same time, Dutch astronomer Willem de Sitter found solutions to Einstein's equations that described an empty universe that was expanding, demonstrating the inherent dynamism of general relativity even without matter. These early theoretical hints, however, were not yet backed by direct observational evidence. The first significant observational steps towards understanding cosmic expansion were taken by American astronomer Vesto Slipher. Starting in 1912, Slipher began to measure the spectral lines of light coming from distant nebulae, which were then thought to be gas clouds within our own Milky Way galaxy. He noticed that the light from most of these nebulae was shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift indicated that these objects were moving away from Earth. A smaller number showed blue shift, meaning they were moving towards us. By 1917, Slipher had measured the velocities of 25 such nebulae, and found that almost all of them were receding from us at very high speeds. While Slipher himself did not interpret these redshifts as evidence for a universally expanding cosmos, his meticulous measurements provided the essential data that would later be combined with other discoveries to paint the complete picture of cosmic expansion. At this stage, the true nature of these nebulae as separate galaxies beyond our own was not yet firmly established. The crucial breakthroughs came with the work of Edwin Hubble building on Slipher's observations. Hubble, another American astronomer, made two pivotal contributions. First, using the powerful 100-inch Hooker telescope at Mount Wilson Observatory, he began to resolve individual stars in some of the nearby spiral nebulae. In particular, he identified Cepheid variable stars in the Andromeda Nebula. Cepheid variables are a type of star whose intrinsic brightness fluctuates in a predictable way, and crucially there is a direct relationship between their period of pulsation and their absolute luminosity or true brightness. By comparing the apparent brightness of a Cepheid as seen from Earth with its known absolute brightness, astronomers can accurately calculate its distance. Hubble's measurements of Cepheids in Andromeda conclusively proved that it was not a gas cloud within the Milky Way, but an independent galaxy located far outside our own. This discovery shattered the long-held belief that the Milky Way comprised the entire universe and established the existence of countless other galaxies. Having established that these nebulae were indeed distant galaxies, Hubble then proceeded to combine his distance measurements with Slipher's existing recessional velocity data. In 1929, he published his groundbreaking finding that there was a direct and proportional relationship between the distance of a galaxy from Earth and its recessional velocity. This relationship became famously known as Hubble's law. It states that the farther away a galaxy is, the faster it appears to be moving away from us. Mathematically, this can be expressed very simply, where the velocity is equal to the Hubble constant multiplied by the distance. The Hubble constant represents the rate at which the universe is expanding. This discovery was a monumental paradigm shift. It provided the first compelling observational evidence that the universe was not static but was actively expanding. Understanding redshift is central to comprehending cosmic expansion. When most people think of redshift, they often think of the Doppler effect, which explains why the pitch of an ambulance siren changes as it moves towards or away from you. For sound waves, a moving source compresses the waves ahead of it and stretches them behind it, leading to a higher or lower pitch. A similar effect occurs with light waves. If a light source is moving away from an observer, its light waves are stretched, making them appear redder. If it is moving towards the observer, its light waves are compressed, making them appear bluer. While the Doppler effect explains the redshift of nearby stars and galaxies due to their individual motions through space, the redshift observed from distant galaxies is overwhelmingly due to a different phenomenon called cosmological redshift. Cosmological redshift is not caused by galaxies moving through space, but by the expansion of space itself between the galaxies. Imagine drawing dots on the surface of an uninflated balloon. As you inflate the balloon, the dots move farther apart from each other, not because they are crawling across the balloon surface, but because the surface itself is stretching. Similarly, in the expanding universe, the light waves travelling from a distant galaxy are stretched as the space they are traversing expands. The wavelength of the light increases, shifting it towards the red end of the spectrum. The greater the expansion of space between the emission point and the observation point, the greater the cosmological redshift. Therefore, redshift from distant galaxies serves as a direct measure of how much the universe has expanded since the light was emitted. Observing highly redshifted light means we are looking at light from very distant galaxies that was emitted when the universe was much younger and smaller. Further observational confirmations of cosmic expansion came in later decades, especially with the use of Type Ia supernovae as standard candles. Type Ia supernovae are powerful stellar explosions that occur when a white dwarf star in a binary system accumulates enough matter from its companion to exceed a critical mass limit known as the Chandrasekhar limit. Because they explode at a very consistent mass, their peak intrinsic luminosity, or absolute brightness, is remarkably uniform. This makes them excellent standard candles, meaning their true brightness is known. By comparing their observed apparent brightness with their known absolute brightness, astronomers can determine their distance with high accuracy, even across vast cosmic distances. Observations of Type Ia supernovae at very large redshifts confirmed Hubble's law at greater distances and unexpectedly revealed in the late 1990s that the universe's expansion is not only happening, but is actually accelerating. This led to the revolutionary concept of dark energy, which is thought to be responsible for this accelerating expansion. The discovery of dark energy provided yet another layer of evidence for the dynamic nature of the cosmos and deepened our understanding of its expansion history. The implications of an expanding universe for its past are profound. If the universe is expanding now, it means that in the past it must have been smaller and denser. Tracing this expansion backward in time leads us to a point where all matter and energy were concentrated into an incredibly hot and dense state. This theoretical point is the Big Bang singularity, the conceptual beginning of the universe as we understand it. The expansion implies a dynamic evolving universe rather than a static one. It suggests a finite age for the cosmos and a specific starting point for its observable history. The rate of expansion encapsulated by the Hubble constant allows astronomers to estimate the age of the universe. By inverting the expansion rate, we can approximate how long it has taken for the universe to reach its current size. Early estimates based solely on Hubble's constant were refined over time with the inclusion of factors like the density of matter and the influence of dark energy. Current estimates place the age of the universe at approximately 13.8 billion years, a figure remarkably consistent with various other cosmological measurements. It is crucial to distinguish between the expansion of space itself and the movement of objects through space. While galaxies are moving away from each other, this is not because they are rocketing through a pre-existing empty void. Instead, the very fabric of space-time is stretching and carrying the galaxies along with it. This is why even a galaxy that is gravitationally bound to another, such as the Andromeda Galaxy, which is on a collision course with our Milky Way, can be seen as an exception to the overall cosmic expansion. On local scales, gravity can counteract the expansion pulling objects together. However, on the vast scales of galaxy clusters and beyond, the expansion of space dominates, ensuring that these distant structures move apart. The understanding that the universe has no center and no edge further supports this concept of expanding space. Every observer in every galaxy would see the same pattern of expansion, with distant galaxies receding faster, suggesting that there is no special place in the universe. This is a key aspect of the cosmological principle, which states that on large scales the universe is homogeneous, meaning it is roughly the same everywhere, and isotropic, meaning it looks the same in all directions. Further evidence supporting cosmic expansion comes from observing galaxies at different stages of their evolution. Because light takes time to travel from distant galaxies, when we look far away, we are effectively looking back in time. We see distant, highly redshifted galaxies as they were billions of years ago. Observations show that these early galaxies were generally smaller, less massive and more irregular in shape, compared to the mature spiral and elliptical galaxies we see in our cosmic neighbourhood today. They also had different star formation rates and chemical compositions. This evolution of galaxy populations over cosmic time is precisely what one would expect in an expanding and evolving universe that started from simpler conditions and gradually formed complex structures through gravity. The observation of quasars, which are extremely luminous active galactic nuclei powered by supermassive black holes, also predominantly at high redshift, suggests an era when such energetic phenomena were more common, fitting into a picture of a younger, more active universe. Despite the strong evidence for cosmic expansion, the precise measurement of the Hubble constant remains an area of active research and some debate. Different methods of measurement using various cosmic distance ladders and different types of standard candles yield slightly different values for the Hubble constant, leading to what is sometimes called the Hubble tension. This tension could point to new physics beyond the standard cosmological model, or simply indicate remaining systematic uncertainties in our measurement techniques. Ongoing and future observations with advanced telescopes are aimed at resolving this discrepancy, further refining our understanding of the universe's expansion history and its precise age. The exploration of cosmic expansion also continues to shed light on the mysterious nature of dark energy, which appears to be driving the accelerating expansion. Understanding dark energy is one of the biggest challenges in modern cosmology, with profound implications for the ultimate fate of the universe, whether it will continue to expand indefinitely, become infinitely cold and dilute, or if dark energy itself might change, leading to a different cosmic destiny. The expansion of the universe is not just a scientific fact, but a foundational concept that underpins our entire understanding of the cosmos's past, present, and future. The journey back in time to the earliest moments of our universe reveals a state utterly alien to our everyday experience, a universe incredibly hot, unbelievably dense, and filled with a primordial soup of fundamental particles known as plasma. This epoch represents a crucial stage in cosmic evolution, bridging the gap between the unimaginably extreme conditions of the Big Bang's first fractions of a second and the formation of the first stable atoms. Understanding this early universe plasma is essential for comprehending how the elementary building blocks of matter came into existence, how the fundamental forces began to operate independently, and how the raw ingredients for stars and galaxies were forged. Immediately after the very first fractions of a second following the Big Bang, the universe was a place of unimaginable energy. If we consider the moment after the inflationary epoch, when the universe underwent an incredibly rapid expansion, or perhaps directly after the Planck epoch, where all the fundamental forces were unified, the universe was not empty space, but a cauldron of extreme heat and density. Temperatures soared to billions or even trillions of degrees Celsius, far hotter than the core of any star. At such extreme temperatures, matter as we know it could not exist. Atoms could not form, molecules were impossible, and even the nuclei of atoms would instantly break apart. Instead, the universe was filled with a plasma, a state of matter, where particles are ionized, meaning they carry an electric charge. This plasma was not the familiar hot gas we might encounter in a neon sign or a lightning bolt. It was a far more exotic form, a soup of fundamental particles, protons, neutrons, electrons, and their antiparticle counterparts, as well as countless photons of light. In this early universe plasma, the energy density was extraordinarily high. Everything was so compressed and so hot that particles were constantly interacting, colliding, and transforming into other particles. The universe was completely opaque to light because photons could not travel far without colliding with a free electron or other charged particle. It was like being inside an incredibly thick fog where visibility was essentially zero. The energy of the photons was so immense that they would immediately ionize any atom that tried to form, stripping away its electrons. This constant dance of ionization and recombination meant that the universe remained in this charged plasma state for a significant period. To truly understand this plasma state, it is important to briefly consider the fundamental forces of nature. There are four known fundamental forces: gravity, which governs the attraction between masses and shapes large-scale structures; electromagnetism, which governs interactions between charged particles and is responsible for light-chemical bonds and electricity; the strong nuclear force, which binds quarks together to form protons and neutrons and holds atomic nuclei together; and the weak nuclear force, which is involved in radioactive decay and certain particle interactions. In the extremely hot and dense conditions of the very early universe, it is theorized that these forces were not distinct, but were unified as different manifestations of a single superforce. As the universe expanded and cooled, these forces successively separated or decoupled from each other. Gravity was the first to separate at the Planck epoch, followed by the strong nuclear force, and then the electro-weak force, which later separated into the electromagnetic and weak nuclear forces. The strengths of these forces and the order in which they separated profoundly influenced how particles formed and interacted in the subsequent plasma era. One of the earliest and most exotic phases of this plasma was the quark-gluon plasma. For the first few microseconds after the Big Bang, temperatures were so incredibly high that even protons and neutrons could not exist as stable particles. Instead, the universe was filled with a superheated soup of fundamental particles called quarks and gluons. Quarks are the building blocks of protons and neutrons, while gluons are the force-carrying particles that bind quarks together through the strong nuclear force. In this quark-gluon plasma state, the quarks and gluons were not confined within larger particles, but roamed freely, interacting intensely. This state is thought to have existed briefly until the universe cooled to about 1 trillion degrees Celsius, at which point the strong nuclear force became strong enough to bind quarks together, a process known as hadronization. As the universe cooled further, a critical event occurred: a period of matter, antimatter annihilation. In the very early universe, matter and antimatter were created in almost equal amounts. For every particle like a quark or an electron, there was a corresponding antiparticle, an antiquark or a positron, with the same mass but opposite charge. When a particle and its antiparticle meet, they annihilate each other, converting their mass entirely into energy, usually in the form of photons of light. If matter and antimatter had been perfectly balanced, they would have completely annihilated each other, leaving behind a universe filled only with photons and no matter to form stars, planets, or life. However, observations show that our universe is overwhelmingly composed of matter. This implies that there must have been a tiny imbalance in the early universe. For every billion antimatter particles, there was approximately 1,000,000,001 matter particles. This tiny surplus of matter survived the annihilation epoch and constitutes all the matter we observe in the universe today. This process set the stage for the formation of stable protons and neutrons during the Hadron epoch. After the Hadron epoch, during which protons and neutrons formed the universe, entered the Lepton epoch. During this time, the universe's energy density was still dominated by photons and leptons, which include particles like electrons, positrons, and neutrinos. As the universe continued to expand and cool, the temperature dropped to the point where electrons and positrons also began to annihilate. Similar to the quark annihilation, a tiny excess of electrons survived the annihilation process. Neutrinos, however, being weakly interacting particles, mostly decoupled from the rest of the plasma very early on, forming a cosmic neutrino background that still permeates the universe today, but is extremely difficult to detect. This period also saw the ratio of protons to neutrons being set, which was crucial for subsequent nucleosynthesis. For a significant period, roughly from about 10 seconds to 38,000 years after the Big Bang, the universe was primarily a radiation-dominated era. This means that the energy density of the universe was overwhelmingly dominated by photons of light rather than matter. The expansion rate of the universe during this epoch was dictated by the energy density of these photons. As the universe expanded, the wavelength of these photons stretched and their energy density decreased. While matter was present, it was the dominant presence of these high-energy photons that kept the universe in its plasma state. One of the most critical events that took place within this early universe plasma was primordial nucleosynthesis, or Big Bang nucleosynthesis (BBN). This process occurred when the universe was only a few minutes old, specifically between about 3 minutes and 20 minutes after the Big Bang. At this point, the universe had cooled to temperatures around 1 billion degrees Celsius, still incredibly hot, but cool enough for protons and neutrons to begin to fuse together to form light atomic nuclei. During this brief window, the strong nuclear force allowed protons and neutrons to combine, forming deuterium, which is an isotope of hydrogen containing 1 proton and 1 neutron. Deuterium then quickly fused to form helium-3 and helium-4, the most abundant isotope of helium. Trace amounts of lithium-7 also formed. The temperature dropped too rapidly for heavier elements like carbon or oxygen to form through fusion. The exact proportions of these light elements depended sensitively on the conditions of the early universe, particularly the ratio of protons to neutrons, and the overall density of baryonic or ordinary matter. The remarkable agreement between the observed abundances of these light elements in the universe today and the predictions of Big Bang nucleosynthesis is one of the strongest pillars of the Big Bang model. Throughout this entire plasma era, from the quark-gluon soup to the period of nucleosynthesis, the universe remained fundamentally opaque. Because electrons were not yet bound to atomic nuclei, they were free to move independently. Photons of light could not travel far without colliding with these free electrons. This constant interaction meant that the universe was like an incredibly dense fog or a thick soup of charged particles and light. Any light emitted would be immediately scattered or absorbed, keeping the universe in a state where it was impossible for light to propagate freely. This opacity is a key characteristic of the early universe plasma. The end of the plasma era and the transition to a transparent universe occurred approximately 38,000 years after the Big Bang. By this time, the universe had expanded and cooled significantly, reaching a temperature of about 3000 Kelvin, roughly the surface temperature of a cool star. At this critical temperature, the energy of the photons was no longer sufficient to keep hydrogen and helium nuclei ionized. Electrons could now combine with these nuclei to form stable, electrically neutral atoms of hydrogen and helium. This event is known as recombination, even though it was the first time these particles combined, not a recombination. Once the electrons were bound in neutral atoms, the photons were no longer constantly interacting with free-charged particles. These photons were now free to travel across the universe unimpeded. This event is called photon decoupling, and the vast bath of these decoupled photons constitutes the cosmic microwave background CMB radiation. The CMB provides a direct snapshot of the universe when it was in its plasma state, serving as a powerful observational window into the conditions of the very early cosmos. The patterns and slight temperature variations in the CMB reveal the initial tiny density fluctuations that would later grow through gravity to form all the large-scale structures we see in the universe today. The transition from an opaque plasma to a transparent universe marked the end of the radiation-dominated era and the beginning of the matter-dominated era. This also led to the cosmic dark ages, a period where no new light sources existed until gravity finally pulled matter together to form the first stars and galaxies. The early universe plasma was thus the crucible in which the fundamental forces separated the basic particles formed and the initial conditions were set for the vast and complex universe we inhabit. The universe in its earliest moments was a place of extraordinary energy, a realm where familiar matter as we know it had not yet fully coalesced. Following the unimaginably rapid expansion during the inflationary epoch, or the conceptual start from the Planck era, the cosmos was a superheated soup of fundamental particles and energy. This period marks the crucial transition where the raw energy of the Big Bang began to transform into the elementary building blocks of everything that would follow from protons and neutrons to stars and galaxies. Understanding how these fundamental particles emerge from this high-energy soup requires delving into the principles of quantum physics and the behavior of matter at extreme conditions. In the very early universe, radiation dominated. Photons, the particles of light, possessed immense energy due to the extremely high temperatures. According to Albert Einstein's famous equation, E equals mc squared, energy and mass are interchangeable. This principle is fundamental to particle formation in the early universe. When photons carry enough energy, they can spontaneously convert into particle-antiparticle pairs. For example, a high-energy photon can transform into an electron, and its antiparticle a positron. Conversely, when a particle meets its antiparticle, they annihilate each other, converting their mass back into energy in the form of photons. This constant creation and annihilation was the prevailing state of affairs in the universe's initial moments. As the universe expanded, it cooled. The temperature of the cosmos dictated which types of particles could be readily created. Only photons with energy exceeding the combined rest mass energy of a particle-antiparticle pair could produce that pair. In the earliest fractions of a second, when temperatures were highest, even the most massive fundamental particles could be created. As the temperature dropped, only lighter particles could be continuously produced. This dynamic process meant that the universe was a bustling environment of particle production and destruction, constantly in thermal equilibrium, where creation and annihilation rates were balanced. Theoretical physics suggests that at incredibly high energies, beyond what we can replicate in particle accelerators today, the fundamental forces of nature may have been unified. This concept is explored in grand unified theories, or GUITs, which propose that the strong nuclear force, the weak nuclear force and the electromagnetic force were once aspects of a single unified force. Gravity would have separated from this superforce even earlier during the Planck epoch. As the universe cooled and its energy density dropped, these unified forces would have successively decoupled from each other, manifesting as the distinct forces we recognize today. The separation of the strong force from the electro-weak force, for instance, would have played a pivotal role in the subsequent formation of protons and neutrons. The breaking of this grand unified symmetry would have released enormous amounts of energy, contributing to the universe's overall energy budget and influencing particle interactions. The primary constituents of the early universe from which all other matter would form are quarks and leptons. These are considered fundamental particles, meaning they are not known to be made of any smaller components. There are 6 types or flavors of quarks: up, down, charm, strange, top and bottom. Quarks also possess a property called color charge, which is related to the strong nuclear force. Protons and neutrons are made up of combinations of quarks. For example, a proton consists of 2 up quarks and 1 down quark, while a neutron is composed of 1 up quark and 2 down quarks. Leptons are another family of fundamental particles. The most familiar lepton is the electron, which carries a negative electric charge. Other leptons include the muon and the tau, which are heavier cousins of the electron, and 3 types of neutrinos: the electron neutrino, muon neutrino, and tau neutrino, which are electrically neutral and interact very weakly with other matter. In the very first moments after the Big Bang, when temperatures were extraordinarily high and particles were constantly being created and annihilated, the universe was a hot, dense soup of quarks, gluons, and leptons, along with their corresponding antiparticles. This state is often referred to as the quark-gluon plasma. In this plasma, quarks were not confined within protons and neutrons. The strong nuclear force which binds quarks together was not yet strong enough to overcome the high kinetic energy of the individual quarks. They moved freely, interacting through the exchange of gluons, which are the force-carrying particles for the strong nuclear force. This state persisted for only a tiny fraction of a second, as the universe continued its rapid expansion and cooling. As the universe expanded further and the temperature dropped to about 1 trillion degrees Celsius, a critical transition occurred. This temperature was low enough for the strong nuclear force to become dominant, leading to the confinement of quarks. This process is known as hadronization. Quarks could no longer exist independently. Instead, they bound together to form composite particles called hadrons. The most important hadrons for the early universe were protons and neutrons, which belong to a class of hadrons called baryons, because they are made of 3 quarks. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. This event marked the transition from a quark-gluon plasma to a universe filled with hadronic matter. A profound mystery that arises during this period is the question of baryogenesis, the origin of the observed matter-antimatter asymmetry in the universe. In the extremely hot conditions of the early universe, fundamental particles and their antiparticles should have been created in almost perfectly equal amounts. For example, for every quark, there should have been an antiquark, and for every electron, a positron. If this balance were truly perfect, then as the universe cooled and particles and antiparticles annihilated each other, converting back into energy, the universe would have ended up as a vast sea of photons with virtually no matter left over. However, our universe is clearly composed almost entirely of matter. Stars, planets, galaxies, and all life are made of matter. This means there must have been a tiny imbalance, a slight excess of matter, particles over antimatter particles in the very early universe. Physicist Andrei Sakharov in 1967 outlined 3 fundamental conditions necessary for baryogenesis to occur, and for a matter-antimatter asymmetry to arise from an initially symmetric state. First, there must be baryon number violation, meaning processes that can change the net number of baryons, which are particles like protons and neutrons. Second, there must be C and CP violation, which refers to violations of charge conjugation symmetry and combined charge parity symmetry. These symmetries essentially state that physical laws should be the same for particles and antiparticles, and for particles mirrored in space. If these symmetries are violated, then matter and antimatter can decay or interact differently. Third, there must be out of equilibrium processes, meaning that the universe was expanding and cooling so rapidly that particle interactions could not maintain thermal equilibrium, allowing the matter-antimatter asymmetry to freeze in. While the exact mechanism for baryogenesis is still an active area of research in theoretical physics, various models exist, including those involving grand unified theories or electroweak baryogenesis, but the precise details remain elusive. Regardless of the exact mechanism, the outcome was crucial for existence. A slight excess of matter survived the annihilation epoch, providing the raw material for everything that formed later. After the quarks were confined into protons and neutrons, the universe continued to cool. Electrons and their antiparticles positrons were still abundant. Like the quarks, electrons and positrons were also constantly being created from energetic photons, and then annihilating each other. As the temperature dropped further below the energy threshold required for their production, the remaining electrons and positrons underwent a final wave of annihilation. Just as with the quarks, a tiny surplus of electrons survived this annihilation thanks to similar asymmetry mechanisms that apply to leptons. These surviving electrons would later combine with the newly formed atomic nuclei. Neutrinos, being very weakly interacting particles, essentially stopped interacting with the rest of the matter and radiation in the early universe much earlier than electrons. They decoupled, forming a cosmic neutrino background that still permeates the universe. Today, a faint relic of the lepton epoch that is incredibly challenging to detect. The relative abundance of fundamental particles, specifically the ratio of protons to neutrons, was crucial for the subsequent formation of light elements. Initially, when temperatures were extremely high and the weak nuclear force was active, protons and neutrons could interconvert through interactions involving neutrinos and positrons. For instance, a proton could absorb a positron and convert into a neutron and a neutrino, while a neutron could decay into a proton, an electron and an antineutrino. These reactions kept the numbers of protons and neutrons roughly equal. However, as the universe cooled and the weak interactions became less frequent, neutrons, which are slightly more massive than protons, began to decay into protons, electrons, and antineutrinos at a faster rate than protons could convert into neutrons. This process led to a shift in the neutron-to-proton ratio. By the time the universe was about 1 second old, the temperature had dropped to approximately 10 billion degrees Celsius. At this point, the weak interactions effectively froze out, meaning they became too slow to maintain the equilibrium between protons and neutrons. The neutron-to-proton ratio settled at about 1 neutron for every 6 or 7 protons. This specific ratio was critically important because virtually all surviving neutrons would eventually be incorporated into helium nuclei during the process of Big Bang nucleosynthesis. The remaining protons would form the vast majority of hydrogen nuclei. The universe at this stage was essentially a hot dense plasma consisting primarily of free protons, free neutrons, free electrons, and a sea of high-energy photons. The stage was now set for the next major event in the early universe, the formation of the first light atomic nuclei. Even after the fundamental particles had formed and their relative abundances were established, photons still dominated the energy density of the universe. The universe was in what is known as the radiation-dominated era, where the expansion rate was primarily controlled by the energy density of light. These photons continued to constantly interact with the free-charged particles, like protons and electrons, preventing the formation of neutral atoms and keeping the universe opaque until it cooled down much further. The formation of these fundamental particles from a high-energy soup was the essential prerequisite for all subsequent cosmic evolution. The story of the universe's evolution continues from a hot dense plasma of fundamental particles to the formation of the first atomic nuclei, a process known as Big Bang nucleosynthesis, or BBN. This epoch, which occurred just a few minutes after the conceptual Big Bang, is profoundly significant because it explains the observed cosmic abundances of the lightest elements, hydrogen, helium and lithium, providing one of the strongest pillars of evidence for the entire Big Bang model. Unlike the formation of heavier elements, which takes place inside stars over billions of years, the primordial elements were forged rapidly in the furnace of the early universe under very specific and extreme conditions. For nucleosynthesis to occur, the universe needed to meet precise temperature and density conditions. It had to be hot enough for nuclear fusion reactions to take place, but also cool enough for newly formed nuclei to remain stable without being immediately broken apart by energetic photons. This crucial window of opportunity opened when the universe was approximately 3 minutes old and lasted for only about 17 minutes until the universe was roughly 20 minutes old. During this brief period, the temperature of the cosmos had dropped to about 1 billion degrees Celsius. This temperature was still incredibly high, but sufficiently cool compared to earlier moments to allow for nuclear binding. The density of the universe was also critical, high enough for protons and neutrons to collide and fuse, but not so high that all available neutrons were immediately consumed in reactions, which would have led to an imbalance. The continuous expansion and cooling of the universe played a vital role in setting the precise conditions and eventually halting the nucleosynthesis process. At the onset of Big Bang nucleosynthesis, the universe was primarily composed of free protons and free neutrons, along with a vast sea of electrons and photons. Protons are simply the nuclei of hydrogen atoms, the simplest element. Neutrons, on the other hand, are slightly more massive than protons, and are unstable when they are free, meaning not bound within an atomic nucleus. A free neutron will spontaneously decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. In the very early universe before nucleosynthesis began, the weak nuclear force facilitated constant interconversion between protons and neutrons. Reactions like a proton absorbing an electron and becoming a neutron, or a neutron decaying into a proton, kept their numbers in equilibrium. However, as the universe cooled and expanded, the weak interactions became less frequent. By the time the universe was approximately 1 second old, and the temperature had dropped to about 10 billion degrees Celsius, the weak interactions essentially froze out. This meant that the interconversion between protons and neutrons slowed down dramatically. Because neutrons are slightly heavier than protons, and also undergo spontaneous decay, the balance shifted. For every 1 neutron, there were roughly 6 or 7 protons. This precise neutron-to-proton ratio, roughly 1 to 7, was absolutely critical for the subsequent formation of the light elements. If there had been significantly more neutrons, more helium would have formed. If there had been fewer, or if neutrons decayed faster, then less helium would have formed. The specific ratio determined the ultimate elemental composition of the universe before stars began to form. The first step in Big Bang nucleosynthesis, the formation of deuterium, the isotope of hydrogen with 1 proton and 1 neutron, presented a significant challenge known as the deuterium bottleneck. Deuterium is a relatively fragile nucleus. In the early moments of the universe, even after the neutron-to-proton ratio froze out, the temperature was still so high that any deuterium that formed would be immediately broken apart by energetic photons. It was like trying to build a sandcastle on a beach being constantly hit by giant waves. The universe needed to cool down sufficiently for deuterium to survive for a long enough period to participate in further nuclear reactions. This deuterium bottleneck effectively delayed the onset of significant nucleosynthesis until the universe was about 3 minutes old, when the temperature had dropped to around 1 billion degrees Celsius. At this temperature, deuterium nuclei became stable enough to withstand the photon barrage. Once deuterium could survive, the floodgates of nuclear fusion opened rapidly. The reactions proceeded quickly, converting almost all of the available neutrons into helium-4 nuclei. Deuterium nuclei would fuse with protons to form helium-3. Deuterium nuclei could also fuse with other deuterium nuclei to form helium-3 plus a neutron, or tritium, which is an isotope of hydrogen with 1 proton and 2 neutrons. The helium-3 and tritium then quickly combined to form helium-4, which is a very stable nucleus consisting of 2 protons and 2 neutrons. Because helium-4 is so stable, and the reactions to form it are efficient, virtually all of the neutrons that survived the early neutron decay and were present when nucleosynthesis began ended up locked inside helium-4 nuclei. This process led to a remarkable prediction. The universe should have started with a primordial composition of roughly 75% hydrogen and 25% helium-4 by mass. This percentage is a direct consequence of the 1 to 7 neutron-to-proton ratio, established earlier as for every 2 protons that make up a hydrogen nucleus, there are 2 protons and 2 neutrons that form a helium-4 nucleus. The remaining protons are just hydrogen nuclei. While hydrogen and helium-4 were the dominant products of Big Bang nucleosynthesis, trace amounts of other light elements were also formed. A small quantity of lithium-7 was produced through a couple of reaction pathways, including the fusion of helium-4 and tritium or beryllium-7, which subsequently decays into lithium-7. However, the amount of these heavier elements formed was extremely small. The conditions in the early universe were simply not suitable for the creation of elements beyond lithium. There are no stable nuclei with atomic masses of 5 or 8, which effectively creates a mass gap, preventing further fusion. For example, if a helium-4 nucleus tried to fuse with a proton or a neutron, it would form an unstable nucleus that would immediately decay. To bridge this gap and form heavier elements like carbon, oxygen, and iron requires a very different set of conditions found only inside stars, where temperatures and densities can be maintained for extended periods, allowing for complex multi-step nuclear reactions. The rapid cooling and expansion of the early universe meant that the nucleosynthesis process stopped after only a few minutes, locking in the primordial abundances of hydrogen, helium, and lithium. The predictions of Big Bang nucleosynthesis are not just theoretical exercises, they are remarkably consistent with observational evidence gathered from various parts of the cosmos. To measure the primordial abundances of these light elements, astronomers look for environments that are as pristine as possible, meaning they have not been significantly contaminated by elements produced later in stars. This often involves observing very old dwarf galaxies or distant gas clouds that show very few heavy elements. For instance, the abundance of deuterium is typically measured by observing the absorption lines in the spectra of light from distant quasars which pass through intervening clouds of primordial gas. The helium-4 abundance is measured in the gas clouds of the most metal-poor blue compact dwarf galaxies, where star formation has been minimal. Even the trace amounts of lithium-7 are measured in the atmospheres of very old stars in the Milky Way halo, which are thought to have formed from nearly primordial gas. The fact that the observed abundances of hydrogen, deuterium, helium, 3 helium-4 and lithium-7 closely match the precise predictions of Big Bang nucleosynthesis is one of the most powerful pieces of evidence supporting the hot dense early universe scenario described by the Big Bang model. The success of Big Bang nucleosynthesis goes beyond simply explaining the existence of these light elements. It also serves as a powerful constraint on various cosmological parameters. For example, the predicted abundances of the light elements are sensitive to the density of baryonic or ordinary matter in the universe. By comparing the observed abundances with BBN predictions, scientists can determine the cosmic baryon density. This independently confirms the baryon density derived from observations of the cosmic microwave background, a completely different set of data. The agreement between these independent measurements strengthens our confidence in the fundamental parameters of the universe. Furthermore, BBN predictions were sensitive to the number of light neutrino types. Before direct measurements confirmed it, BBN calculations already strongly suggested there are precisely 3 types of light neutrinos, which was later confirmed by particle physics experiments. While Big Bang nucleosynthesis is a triumphant success, there is one persistent anomaly known as the lithium problem. Observations of primordial lithium-7 abundance in very old stars seem to be consistently lower than the predictions of BBN by a factor of about 2 to 3. This discrepancy is a puzzle that remains an active area of research. Possible solutions include inaccuracies in stellar atmosphere models that affect lithium measurements, new physics beyond the standard model that could alter lithium production or destruction in the early universe, or subtle systematic errors in our understanding of the nuclear reactions themselves. Despite this one unresolved issue, the overall agreement of BBN with observations for hydrogen and helium is so compelling that it remains a cornerstone of modern cosmology. The products of Big Bang nucleosynthesis, the bare nuclei of hydrogen and helium, were the basic building blocks that would later form the vast majority of the visible matter in the universe. These nuclei would remain in a hot ionized plasma state until the universe cooled enough for electrons to combine with them, forming neutral atoms and setting the stage for the cosmic dark ages and the eventual formation of stars and galaxies. The cosmic microwave background, or CMB radiation, stands as one of the most compelling pieces of evidence supporting the Big Bang theory, a faint echo of the universe's fiery beginning. It is a pervasive glow of a microwave light filling all of space uniform in all directions and represents a direct snapshot of the universe when it was only about 38,000 years old. Its discovery and subsequent detailed study have revolutionized our understanding of cosmology, revealing not only the universe's past but also its fundamental properties and composition. The existence of a cosmic background radiation was first theoretically predicted in the mid-20th century. In the late 1940s, physicists George Gamow, Ralph Alpher and Robert Herman, working on Big Bang nucleosynthesis, proposed that if the universe began in an incredibly hot and dense state, then as it expanded and cooled, there should be a leftover glow of radiation permeating space today. They reasoned that this radiation would have cooled significantly over billions of years due to the universe's expansion, shifting its wavelength from visible light to much longer microwave wavelengths. They even estimated its temperature to be a few Kelvin above absolute zero. Their prediction was based on the idea that the early universe would have been so hot and dense that matter and radiation would have been tightly coupled, interacting constantly, creating an opaque plasma. As the universe expanded and cooled, a critical point would be reached where matter and radiation would decouple, allowing the radiation to travel freely. This surface of last scattering would imprint its characteristics on the escaping photons. Despite these predictions, the cosmic microwave background was discovered quite by accident in 1964 by two American radio astronomers, Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories in Holmdel, New Jersey. They were conducting tests on a large horn antenna originally built for satellite communication experiments. Their goal was to detect faint radio waves reflected off balloon satellites. However, no matter where they pointed the antenna, they detected a persistent low-level hiss or static that seemed to come uniformly from all directions in the sky. This noise was equivalent to a temperature of about 3.5 Kelvin. Puzzled by this persistent signal, they meticulously tried to identify and eliminate all possible sources of interference. They cleaned the antenna, removing what they famously described as white dielectric material left by pigeons nesting inside it. They checked for radar interference military signals and even radio broadcasts from New York City, but the noise persisted always there, always uniform. Unaware of the theoretical predictions, Penzias and Wilson were at a loss to explain the mysterious signal. Coincidentally, a group of physicists at Princeton University led by Robert Dicke was independently working on a project to search for exactly this kind of cosmic background radiation, as predicted by Big Bang theory. They were preparing to build their own antenna to detect it. When Penzias and Wilson contacted Dicke to discuss their unexplained noise, Dicke immediately realized what they had stumbled upon. He famously told his colleagues, "Boys, we've been scooped." The persistent uniform microwave hiss detected by Penzias and Wilson was indeed the cosmic microwave background radiation, the cooled-down afterglow of the Big Bang. This accidental discovery provided powerful observational confirmation of the Big Bang model and earned Penzias and Wilson the Nobel Prize in Physics in 1978. The cosmic microwave background exhibits several fundamental properties that are crucial to its significance. Firstly, its spectrum is an almost perfect blackbody spectrum. A blackbody is an idealized object that absorbs all incident electromagnetic radiation and emits radiation at a characteristic spectrum that depends only on its temperature. The CMB's blackbody curve is a hallmark of thermal equilibrium, indicating that the radiation originated from a state where matter and radiation were in complete balance. This is precisely what is expected from a hot, dense early universe. Secondly, its temperature is precisely measured to be about 2.7 to 25 Kelvin, just under 3 degrees above absolute zero. This exceedingly cold temperature is a result of the universe's expansion over 13.8 billion years, which has stretched the original high-energy photons to much longer lower-energy microwave wavelengths. Thirdly, the CMB is remarkably isotropic, meaning it is almost perfectly uniform in temperature across the entire sky. This uniformity indicates that the early universe was incredibly smooth and homogeneous, on large scales a crucial piece of information for understanding subsequent structure formation. The CMB is a direct witness to a pivotal moment in the universe's history known as the Recombination epoch, or the surface of last scattering. Before this epoch, which occurred approximately 38,000 years after the Big Bang, the universe was a hot, dense, opaque plasma. Temperatures were so high that electrons were not bound to atomic nuclei. Instead, electrons and atomic nuclei, mostly protons and helium nuclei, existed as a free sea of charged particles. Photons of light were constantly scattering off these free charged particles, preventing light from travelling far without being absorbed or deflected. The universe was effectively opaque, like a very thick fog. As the universe continued to expand and cool, its temperature eventually dropped to around 3000 Kelvin. At this critical temperature, electrons had sufficiently low energy that they could combine with the atomic nuclei to form stable, electrically neutral atoms of hydrogen and helium. Once electrons were bound in atoms, the universe underwent a dramatic transformation. The free charged particles were largely gone, and photons were no longer constantly interacting with them. The universe suddenly became transparent, allowing photons to travel freely through space for the first time. These photons, which were emitted at the time of recombination, are the cosmic microwave background radiation we observe today. We're essentially looking back in time to the moment when the universe first became transparent to light, hence the term surface of last scattering. The existence and properties of the CMB provide incredibly strong and direct evidence for the Big Bang theory. Its blackbody spectrum at 2.725 Kelvin is exactly what would be expected from the cooled-down remnant of a hot Big Bang. The remarkable uniformity of the CMB across the sky confirms the cosmological principle that the universe is homogeneous and isotropic on large scales. Furthermore, the CMB decisively disproved the steady-state theory, which proposed a continuously creating but unchanging universe, as such a theory could not account for the observed background radiation. The CMB is not just a confirmation, but a foundational pillar upon which modern cosmology rests, providing an indispensable link to the universe's infancy. While the CMB is remarkably uniform, its true power lies in its tiny variations. Initial observations like those by Penzias and Wilson found the CMB to be almost perfectly smooth. However, theoretical models of structure formation predicted that there must be small temperature fluctuations in the CMB. Without these tiny variations, the universe would have remained perfectly smooth and uniform, and gravity would have had no starting points to begin forming the large-scale structures like galaxies and galaxy clusters we see today. In 1992, the Cosmic Background Explorer or COBE satellite made a groundbreaking discovery. After meticulously mapping the entire sky, COBE detected incredibly subtle temperature variations in the CMB at a level of about 1 part in 100,000. These tiny anisotropies or directional variations were exactly what cosmologists were hoping to find. They represented the primordial density fluctuations in the early universe, the seeds from which all cosmic structures would eventually grow through the action of gravity. The significance of these CMB anisotropies cannot be overstated. They are direct evidence of slight overdense and underdense regions in the universe at the time of recombination. Overdense regions were slightly hotter, while underdense regions were slightly cooler. These subtle differences in density meant that gravity would act slightly more strongly in the overdense areas, attracting more matter over billions of years. Conversely, underdense regions would lose matter to their denser surroundings. This gravitational instability provided the positive feedback mechanism necessary for initial tiny fluctuations to grow into the vast cosmic structures we observe today. The existence and precise characteristics of these anisotropies also provided strong support for the theory of cosmic inflation. Inflation predicts that quantum fluctuations in the very early universe would have been stretched to cosmic scales, creating precisely the kind of nearly scale-invariant primordial density fluctuations observed in the CMB. Following COBE, a new generation of dedicated CMB satellites provided increasingly precise measurements of these anisotropies. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, produced a significantly higher resolution map of the CMB anisotropies, further confirming the COBE findings and providing much more detailed information. Then the European Space Agency's Planck satellite, launched in 2009, delivered the most precise and detailed map of the CMB to date, with unprecedented resolution and sensitivity. These missions meticulously mapped the temperature variations across the entire sky, allowing cosmologists to analyze the statistical properties of these fluctuations in exquisite detail. The patterns of these tiny temperature variations in the CMB are not random. They contain a wealth of information about the universe's fundamental properties. The observed peaks and troughs in the CMB power spectrum, which is a statistical representation of the CMB anisotropies, correspond to acoustic oscillations or sound waves that propagated through the hot, dense plasma of the early universe before recombination. As matter and radiation were tightly coupled, the photons created pressure waves. When the universe became transparent, these sound waves were frozen in place, leaving their imprint on the CMB. By analysing the precise positions and heights of these peaks and troughs, cosmologists have been able to determine fundamental cosmological parameters with remarkable accuracy. These parameters include the geometry of the universe, confirming that it is almost perfectly flat, its age, its expansion rate, and the relative densities of ordinary matter, and dark energy. For example, the first peak in the CMB power spectrum strongly supports a flat geometry for the universe, meaning that parallel lines remain parallel, a result with profound implications for the universe's large-scale structure. Beyond temperature anisotropies, the CMB also exhibits polarization. Just as light waves can be polarized in specific directions, the CMB photons also carry information about their polarization. There are two main types of CMB polarization, E modes and B modes. E modes are generated by density variations in the early universe and have been robustly detected. B modes, however, are more elusive. They can be generated by two mechanisms: the lensing of E modes by foreground galaxy clusters, which distorts the light on its journey to us, or more excitingly by primordial gravitational waves created during the inflationary epoch. Detecting primordial B modes would provide direct evidence for inflation and probe physics at incredibly high energies in the universe's infancy. While lensing B modes have been detected, the search for primordial B modes is an ongoing frontier of CMB research, aiming to unlock secrets of the very first moments of the Big Bang. The CMB map, with its hotspots and cold spots, essentially provides a cosmological blueprint. The slightly hotter regions represent areas where the universe was slightly denser and would eventually grow to become clusters of galaxies. The slightly colder regions were underdense and would evolve into cosmic voids. It is the furthest back in time we can see directly, as the universe was opaque before the CMB was released. We cannot see beyond the surface of last scattering, because any light emitted before that time would have been immediately scattered by the dense plasma. The CMB also allows cosmologists to precisely constrain the age of the universe at about 13.8 billion years, and confirms its composition with roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The cosmic microwave background continues to be an invaluable tool for cosmologists, offering a wealth of information about the Big Bang, its initial conditions, and the fundamental properties that govern our universe. Its study remains at the forefront of cosmological research, continually refining our understanding of the cosmos. The universe at its birth, as revealed by the cosmic microwave background, was remarkably smooth and uniform. Yet when we look around us today, we observe a universe filled with intricate and massive structures. Stars clustered into galaxies, galaxies grouped into clusters, and these clusters arranged in vast cosmic filaments, separated by immense empty voids. This striking transformation from a nearly homogeneous early state to the highly clumpy universe we inhabit is one of the most compelling narratives in cosmology. The primary sculptor behind this grand cosmic architecture is gravity acting on tiny initial density variations in the primordial universe. The challenge of explaining how such a smooth early universe could evolve into a structured one was a significant problem for cosmologists. If the universe had been perfectly uniform at the time the cosmic microwave background was released, then gravity would have nothing to act upon to create the inhomogeneities we see. A perfectly smooth distribution of matter would remain perfectly smooth as it expanded. Therefore, the existence of galaxies and galaxy clusters today unequivocally points to the presence of initial imperfections, tiny seeds of structure that were present in the very early universe. These seeds are precisely what were detected as the faint temperature anisotropies, or variations in the cosmic microwave background. These are regions where the density of matter was ever so slightly higher or lower than the average. These minute differences measured in parts per 100,000 were the starting points for all the large-scale structures we observe. The origin of these primordial density fluctuations is deeply tied to the physics of the very early universe, particularly the theory of cosmic inflation. Inflation posits that in the first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid and exponential expansion. During this rapid stretching, quantum fluctuations, which are tiny random variations in energy that constantly occur at the subatomic level, were stretched to astronomical scales. These quantum fluctuations became the macroscopic density variations that eventually imprinted themselves on the cosmic microwave background. In essence, inflation took quantum fuzziness and blew it up to cosmic proportions, providing the initial gravitational imperfections necessary for structure formation. Once these tiny density variations were established, the universal force of gravity began its patient work. Overdense regions, those areas with slightly more matter than average, exerted a slightly stronger gravitational pull on their surroundings. This stronger gravity would then attract even more matter from the slightly less dense regions around them. As matter flowed into these overdense areas, they became even denser, and their gravitational pull grew even stronger. This process is a classic example of gravitational instability, a positive feedback loop where denser regions grow denser and rarer regions become rarer. The initial tiny fluctuations were amplified over billions of years of cosmic evolution, leading to the formation of the large-scale structures we see. A crucial player in this process of structure formation is dark matter. Ordinary matter, also known as baryonic matter, the stuff that makes up stars, planets, and us, interacts strongly with radiation through electromagnetic forces. In the early universe before recombination, when the universe was an opaque plasma, photons were constantly scattering off free electrons and protons. This tight coupling between ordinary matter and radiation meant that any small density variations in ordinary matter would be quickly smoothed out by the pressure of the photons. It was like trying to create a lump in a very energetic fluid. The pressure would immediately flatten it. If only ordinary matter existed, structure formation would have been severely hampered, and the large-scale structures we observe would not have had enough time to form. However, dark matter behaves very differently. It does not interact with light or other electromagnetic radiation, which is why it is called dark. It only interacts through gravity. Therefore, dark matter was not subject to the smoothing effects of radiation pressure in the early universe. This meant that the density fluctuations in dark matter could begin to grow much earlier than those in ordinary matter even before the recombination epoch. Dark matter fluctuations acted as the gravitational scaffolding or potential wells into which ordinary matter would later fall. This fundamental difference in behavior between dark matter and ordinary matter is essential for explaining the observed distribution of galaxies. Without dark matter, the universe would look very different, perhaps a much more uniform and less structured place. As dark matter fluctuations grew through gravitational instability, they formed large gravitationally bound clumps called dark matter halos. These halos are not visible directly, but their gravitational influence can be inferred from how they affect the rotation of galaxies and the bending of light from distant objects through a phenomenon called gravitational lensing. These dark matter halos served as the cosmic nurseries for galaxy formation. After the recombination epoch, when the universe cooled sufficiently for electrons to combine with protons and helium nuclei to form neutral atoms, ordinary matter decoupled from radiation. Now that ordinary matter was no longer tightly coupled to photons, it could fall into the gravitational potential wells created by the pre-existing dark matter halos. This process allowed ordinary gas to accumulate and eventually collapse to form stars and galaxies within these dark matter structures. The process of structure formation is fundamentally hierarchical or bottom-up. This means that smaller structures formed first and then gradually merged and accreted to form larger ones. Tiny initial dark matter clumps grew and merged to form mini-halos. Within these mini-halos, the first stars formed known as population 3 stars. These very first stars were massive, short-lived, and played a crucial role in ionizing the neutral hydrogen gas that filled the universe after recombination. These smaller structures continued to merge, forming dwarf galaxies and then larger galaxies. Galaxies in turn clustered together to form galaxy groups, and then massive galaxy clusters. This continuous process of merging and accretion builds up the cosmic structures over billions of years. As the hierarchical clustering unfolded, gravity sculpted the universe into a vast and intricate network known as the cosmic web. Cosmological simulations which track the gravitational interactions of billions of particles in a virtual universe consistently reproduce this striking large-scale structure. The cosmic web consists of dense knots, where galaxy clusters reside, elongated filaments of galaxies connecting these knots, and vast empty regions called voids, where very few galaxies are found. This simulated cosmic web remarkably matches the observed distribution of galaxies in large-scale surveys, providing powerful evidence for our understanding of structure formation. Galaxies are not randomly scattered throughout space, but are organized along these filaments and concentrated at their intersections, forming the backbone of the universe's structure. Within the dark matter halos that populate the cosmic web, ordinary gas cooled and collapsed, leading to the formation of galaxies. As gas clouds collapsed, their density increased and eventually ignited star formation. The evolution of galaxies is a complex interplay of star formation feedback from supernovae explosions and active supermassive black holes, galactic winds and mergers with other galaxies. Early galaxies typically appear smaller, more irregular and chemically poorer than the mature spiral and elliptical galaxies we see today. Over billions of years, these smaller galaxies merged and accreted gas, shaping their morphology and enriching their chemical composition through successive generations of stars. Galaxy clusters are the largest gravitationally bound structures in the universe, typically containing hundreds or even thousands of galaxies. These massive structures are predominantly composed of dark matter, with galaxies residing in their gravitational potential wells and hot X-ray emitting gas filling the space between the galaxies, a relic of their violent formation history. While gravity is the primary architect of structure formation, the influence of dark energy must also be considered, especially on the larger scales. Dark energy is the mysterious component of the universe that is causing its expansion to accelerate. At smaller scales, like within galaxies or even galaxy clusters, gravity remains dominant, pulling matter together. However, on very large scales exceeding roughly a few 100 million light-years, the repulsive effect of dark energy starts to counteract gravity's pull. This means that dark energy effectively limits the growth of the largest possible structures. It prevents very distant galaxy clusters from merging to form even larger structures, and contributes to the accelerating expansion that will eventually carry very distant galaxies out of our observable horizon, making them causally disconnected from us. The interplay between gravity and dark energy shapes the universe's ultimate destiny, determining whether structure formation continues or eventually slows as the universe becomes more dilute. Cosmological simulations have become an indispensable tool for understanding structure formation. These n-body simulations typically use supercomputers to track the gravitational interactions of millions or even billions of dark matter particles, and sometimes also include baryonic matter over cosmic timescales. By starting with the initial tiny density fluctuations observed in the CMB, these simulations can accurately reproduce the evolution of the cosmic web, the formation of dark matter halos, and the clustering of galaxies on large scales. They allow cosmologists to test different models of dark matter and dark energy, and to explore various scenarios for galaxy formation. Beyond simulations, observational probes like large-scale galaxy surveys such as the Sloan Digital Sky Survey, weak gravitational lensing which maps the distribution of dark matter by observing how it distorts the light from background galaxies, and X-ray observations of the hot gas in galaxy clusters all provide crucial data that supports and refines our understanding of how cosmic structures formed under the relentless pull of gravity. Despite these successes, several challenges and open questions remain, such as the missing satellite problem, where simulations predict more small satellite galaxies around large galaxies than are observed, and the cusp core problem regarding the central density profiles of dark matter halos. The visible universe, with its galaxies, stars, and planets, represents only a small fraction of what actually exists. For decades, astronomers and physicists have gathered overwhelming evidence pointing to the presence of a mysterious invisible substance that exerts gravitational influence but does not emit, absorb, or reflect light. This enigmatic component of our cosmos is known as dark matter. Its existence is not directly observed, but is inferred from its profound gravitational effects on the motion of visible matter and the large-scale structure of the universe. Understanding dark matter is crucial because it accounts for roughly 27% of the universe's total mass energy content, dwarfing the mere 5% contributed by ordinary baryonic matter, the stuff that makes up everything we can see and touch. The remaining 68% is dark energy, a topic for later discussion. The first hints of unseen mass emerged in the 1930s from the work of Swiss-American astronomer Fritz Zwicky. While studying the Coma cluster of galaxies, Zwicky measured the velocities of individual galaxies within the cluster. He applied the virial theorem, which relates the kinetic energy of a system to its potential energy, to estimate the total mass of the cluster. His calculations revealed a shocking discrepancy. The gravitational mass required to hold the cluster together and prevent its galaxies from flying apart at their observed speeds was far greater than the mass accounted for by the visible galaxies alone. Zwicky famously coined the term dark matter to describe this missing mass, suggesting that there must be some invisible non-luminous material within the cluster exerting gravitational pull. His findings were initially met with skepticism and were not widely accepted for several decades, partly due to the limitations of observational technology at the time and partly because the idea was so radical. Decades later, in the 1970s, the concept of dark matter gained significant traction thanks to the pioneering work of American astronomer Vera Rubin and her colleagues. Rubin began studying the rotation curves of spiral galaxies. A rotation curve plots the orbital speed of stars or gas at different distances from the galactic center. Based on Newtonian physics and the observed distribution of visible matter in galaxies, astronomers expected that the orbital speeds of stars would decrease as their distance from the galactic center increased, especially beyond the visible edge of the luminous disk. This is similar to how the orbital speed of planets in our solar system decreases with increasing distance from the Sun, as most of the solar system's mass is concentrated in the Sun. However, Rubin and her team consistently found something entirely different. They observed that stars and gas clouds far from the galactic center were orbiting just as fast or even faster than stars closer in. These flat rotation curves indicated that there was a substantial amount of unseen mass extending far beyond the visible boundaries of the galaxy's luminous disk, creating a vast gravitational halo that kept the outer stars in their rapid orbits. This unseen mass could not be explained by ordinary matter in the form of dim stars, gas clouds, or dust, because such matter would still emit some form of radiation or absorb light, making it detectable. The evidence from galaxy rotation curves provided compelling and widespread support for Zwicky's earlier dark matter hypothesis, shifting it from a theoretical curiosity to a widely accepted scientific necessity. Beyond individual galaxies, the evidence for dark matter extends to larger scales such as galaxy clusters. Zwicky's initial observations in the Coma cluster were a testament to this. Modern observations of galaxy clusters continue to bolster the dark matter case. One powerful piece of evidence comes from gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of spacetime, and light rays travelling through this warped spacetime follow curved paths. This phenomenon, known as gravitational lensing, causes the light from distant background galaxies to be distorted, magnified, or even multiply imaged as it passes through the gravitational field of a massive foreground galaxy cluster. By precisely measuring the distortions and amplifications of these background galaxy images, astronomers can reconstruct the total mass distribution of the foreground cluster, including both its visible and invisible components. These gravitational lensing maps consistently show that the total mass of galaxy clusters is far greater than the mass of their visible galaxies and hot gas. The distribution of this inferred mass matches the gravitational wells needed to explain the observed lensing effects, strongly indicating the presence of a dominant dark matter component that extends throughout the cluster. Another line of evidence from galaxy clusters comes from X-ray observations. Galaxy clusters are not just collections of individual galaxies. They also contain vast quantities of extremely hot gas that permeates the space between the galaxies. This gas is so hot that it emits X-rays, which can be detected by X-ray telescopes in space. For this hot gas to remain confined within the cluster and not simply escape into intergalactic space, it must be held in place by a powerful gravitational force. By analysing the temperature and distribution of this X-ray emitting gas, astronomers can determine the gravitational potential well required to contain it. These calculations consistently show that the amount of visible matter in the galaxies and the X-ray gas itself is insufficient to provide the necessary gravitational confinement. An additional source of mass, a substantial amount of dark matter, is required to explain the stability and equilibrium of the hot gas in galaxy clusters. Perhaps one of the most direct and visually striking pieces of evidence for dark matter comes from the Bullet cluster. This cluster is actually two galaxy clusters that have recently passed through each other. When these two clusters collided, the ordinary baryonic matter, which includes the hot X-ray emitting gas, interacted and slowed down due to friction. However, the dark matter, which is thought to interact only very weakly with itself and with ordinary matter, passed straight through largely unimpeded. Observations of the Bullet cluster using X-ray telescopes show that the hot gas is located primarily in the center, between the two original clusters, where it was slowed down by the collision. In contrast, gravitational lensing maps of the cluster show that the vast majority of the mass, including the dark matter, is located at the outskirts of the colliding clusters, precisely where the galaxies are and where the dark matter should have passed through without slowing down. The spatial separation between the visible X-ray gas and the inferred mass distribution provides compelling direct observational evidence for the existence of dark matter as a distinct component of the universe that behaves differently from ordinary matter. The role of dark matter in the formation of cosmic structures is absolutely critical. In the very early universe, about 38,000 years after the Big Bang, the universe was a hot, dense plasma of ordinary matter and radiation. While there were tiny density fluctuations or inhomogeneities present as observed in the cosmic microwave background, these fluctuations in ordinary matter were constantly being smoothed out by the immense pressure of photons. If ordinary matter were the only type of matter present, these fluctuations would have been largely washed away, and there would not have been enough time for the large-scale structures like galaxies and galaxy clusters to form through gravity. The universe would have remained much more uniform and featureless. However, dark matter does not interact with photons or other electromagnetic radiation. It is unaffected by the pressure of radiation. This means that the tiny density fluctuations in dark matter could begin to grow much earlier than those in ordinary matter, even before the universe became transparent. Dark matter fluctuations essentially acted as the gravitational scaffolding, or the gravitational seeds that were able to grow unchecked by radiation pressure. These overdense regions of dark matter gradually accumulated more dark matter through gravity, forming large gravitationally bound clumps called dark matter halos. These halos are invisible themselves, but they created deep gravitational potential wells across the cosmos. Once the universe cooled sufficiently for ordinary matter to form neutral atoms, a process known as recombination, which released the cosmic microwave background radiation, ordinary baryonic matter decoupled from radiation. Now, free from the smoothing effects of photon pressure, the ordinary gas could fall into the pre-existing gravitational wells created by the dark matter halos. As the gas accumulated within these dark matter halos, it became denser and eventually cooled, leading to the formation of the first stars and eventually galaxies. Dark matter provided the necessary gravitational framework and the early start for gravitational collapse, allowing the universe to transition from a relatively smooth state to the highly structured cosmic web we observe today. Without dark matter, the universe's large-scale structure would be fundamentally different, perhaps much less clumpy and structured, and it is highly unlikely that galaxies would have formed in the way they did, or even formed at all within the time frame of our universe's age. The nature of dark matter remains one of the biggest mysteries in modern physics. We know what it is not, but we do not yet know what it is. It is not ordinary baryonic matter, which includes protons, neutrons, and electrons. This is confirmed by Big Bang nucleosynthesis, which accurately predicts the abundance of light elements based on the amount of ordinary matter. If dark matter were baryonic, it would have affected these predictions. Therefore, dark matter must be non-baryonic, meaning it is made of particles that are not part of the standard model of particle physics. Current theoretical models propose various candidates for dark matter particles. The leading candidate is a class of hypothetical particles known as weakly interacting massive particles, or WIMPs. These particles would be massive and would interact very weakly with ordinary matter, primarily through gravity and possibly the weak nuclear force. Their weak interaction would explain why they are so difficult to detect, and why they do not emit or absorb light. Another popular candidate is the axion, a hypothetical extremely light particle, proposed to solve certain problems in quantum chromodynamics, the theory of the strong nuclear force. Other more exotic candidates include sterile neutrinos, primordial black holes, not formed from stellar collapse, or even entirely new fundamental forces. The properties of dark matter also play a crucial role in its ability to form structures. Cosmological simulations strongly favour what is called cold dark matter, or CDM. Cold dark matter particles are defined as moving relatively slowly, so they do not smooth out small-scale density fluctuations. If dark matter were hot, meaning its particles moved at relativistic speeds, it would have streamed out of small overdense regions, washing away small-scale density fluctuations and making it difficult for small galaxies to form. The observed abundance of dwarf galaxies and the detailed structure of galaxies are consistent with cold dark matter. This cold dark matter model combined with the cosmological constant lambda to explain dark energy forms the standard model of cosmology known as lambda CDM. Scientists are actively searching for dark matter particles through various experimental approaches. Direct detection experiments typically involve highly sensitive detectors placed deep underground in mines to shield them from cosmic rays. These detectors aim to observe the rare occasions when a dark matter particle might interact with an atomic nucleus in the detector, producing a tiny recoil that can be measured. Experiments like LuxLZ, Xenon and Pandex are at the forefront of this search, attempting to directly detect WIMPs. Indirect detection experiments look for the products of dark matter annihilation or decay. If dark matter particles are their own antiparticles, or if they decay, they might produce detectable particles like gamma rays, neutrinos or cosmic rays. Telescopes like the Fermi Gamma Ray Space Telescope and ground-based gamma ray observatories search for these signals from regions where dark matter is expected to be abundant, such as the galactic center or dwarf galaxies. Finally, collider experiments such as the Large Hadron Collider at CERN aim to produce dark matter particles directly by smashing known particles together at extremely high energies. If dark matter particles are produced, they would escape the detector without interacting, leaving behind a telltale signature of missing energy and momentum. Despite decades of intense search, dark matter particles have not yet been directly detected, underscoring their elusive nature. The presence and behaviour of dark matter have profound implications for our understanding of the universe. It is not just an obscure hypothetical substance, but an essential ingredient for the cosmos to look the way it does. Dark matter explains the stability of galaxies and galaxy clusters, the flat rotation curves of spiral galaxies, and the gravitational lensing effects observed around massive cosmic structures. It provided the necessary gravitational scaffolding for the early universe's tiny density fluctuations to grow into the vast cosmic web of galaxies and clusters. Without dark matter, our entire cosmological model would fall apart. It is a fundamental component of the universe, driving the formation of the very structures that allow us to exist and observe the cosmos. While its precise nature remains one of the most tantalizing mysteries in science, the evidence for its gravitational influence is overwhelming, making dark matter an indispensable part of our cosmic story. The universe is expanding, a fact firmly established by Edwin Hubble's observations in the late 1920s. For many decades, cosmologists assumed that this expansion, while ongoing, would gradually slow down due to the gravitational pull of all the matter within the universe. It was thought that gravity acting on everything would cause a deceleration, much like a ball thrown upwards slows down as gravity pulls it back. However, in the late 1990s, a groundbreaking discovery completely upended this long-held assumption. Observations of distant supernovae revealed that the universe's expansion is not slowing down, but is in fact accelerating. This astonishing finding pointed to the existence of a mysterious cosmic component with repulsive gravity, now known as dark energy. Dark energy represents approximately 68% of the universe's total mass energy content, making it the dominant component of our cosmos. Its existence and properties profoundly influence the universe's past, present, and future. The concept of a cosmological constant, or a form of energy inherent to space itself, was first introduced by Albert Einstein in 1917 when he was developing his theory of general relativity. As previously mentioned, Einstein initially added this term to his equations to force a static universe, which was the prevailing belief at the time. After Hubble's discovery of the expanding universe, Einstein famously called the cosmological constant his biggest blunder. For decades, the cosmological constant was largely discarded from mainstream cosmology. However, its ghost lingered in the background as a potential explanation for various cosmic phenomena. The reintroduction of a cosmological constant, or a similar form of dark energy, into cosmological models became essential to explain the accelerating expansion. The pivotal evidence for accelerating expansion came from independent studies of Type Ia supernovae conducted by two competing research teams in the late 1990s. These teams were the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees. Both teams were using Type Ia supernovae as standard candles to measure cosmic distances. Type Ia supernovae are powerful stellar explosions that occur when a white dwarf star in a binary system accumulates enough matter from a companion star to exceed a critical mass limit known as the Chandrasekhar limit. Because they explode at this consistent mass, their peak intrinsic luminosity or absolute brightness is remarkably uniform and very high, making them visible across vast cosmic distances. By comparing the observed apparent brightness of a Type Ia supernova with its known absolute brightness, astronomers can accurately determine its distance. This method provides a direct way to measure how much the universe has expanded since the light from the supernova was emitted. Both research teams observed Type Ia supernova in very distant galaxies and found an unexpected result. The distant supernovae were dimmer than they should have been if the universe's expansion was decelerating or even expanding at a constant rate. Their unexpected dimness implied that they were farther away than predicted by a decelerating universe. The only way to explain this additional distance was if the universe's expansion had been accelerating over cosmic time. This meant that the space between us and these distant supernovae had expanded more than expected during the light's journey. The stunning and independent agreement between the two teams led to the groundbreaking conclusion that the universe's expansion is accelerating. This discovery earned Perlmutter, Schmidt and Rees the Nobel Prize in Physics in 2011. Beyond Type Ia supernovae, other lines of evidence consistently support the existence and properties of dark energy. One of the most important comes from the cosmic microwave background, or CMB radiation. The CMB provides a snapshot of the universe when it was only about 38,000 years old. By analysing the precise patterns of temperature fluctuations in the CMB, particularly the locations and heights of its acoustic peaks, cosmologists can determine the overall geometry of the universe and the relative proportions of its energy components, including ordinary matter, and dark energy. The CMB data from missions like WMAP and Planck confirm that the universe is spatially flat, meaning that parallel lines remain parallel on cosmic scales. For a universe to be flat, its total energy density must be equal to a critical density. When astronomers add up the observed densities of ordinary matter and dark matter, they find that they only account for about 32% of the critical density needed for a flat universe. The remaining approximately 68% must be contributed by something else, and that something else is dark energy. The CMB data is remarkably consistent with the supernova observations, reinforcing the conclusion that dark energy is the dominant component of the universe's energy budget. The distribution of a large-scale structure in the universe also provides evidence for dark energy. Dark energy affects the growth of cosmic structures such as galaxies and galaxy clusters. If dark energy were not present, gravity would continue to pull matter together, forming progressively larger and denser structures. However, the repulsive effect of dark energy counteracts gravity on large scales, slowing down the rate at which structures grow. By studying the clustering of galaxies and the abundance of galaxy clusters at different cosmic epochs, astronomers can infer the influence of dark energy. A specific signature in the distribution of galaxies known as baryon acoustic oscillations, or BAOs, acts as a standard ruler in the cosmos. BAOs are fossilized sound waves from the early universe that imprinted a characteristic scale on the distribution of matter. By measuring this characteristic scale at different distances, astronomers can determine the universe's expansion history. Measurements of BAOs from large galaxy surveys independently confirm the accelerating expansion and are consistent with the properties of dark energy derived from supernovae and CMB data. The fundamental characteristic of dark energy that causes cosmic acceleration is its negative pressure. In general relativity, gravity is not just caused by mass, but by energy and pressure as well. Positive pressure like that of ordinary gas creates an attractive gravitational effect. However, a substance with negative pressure creates a repulsive gravitational effect, pushing space-time apart. The vacuum energy, which is a candidate for dark energy, possesses this negative pressure. Imagine if empty space itself had a constant intrinsic energy density. As the universe expands, the volume of space increases, but the energy density of this vacuum energy remains constant because new space is continuously being created with this energy. This property ensures that as the universe expands, the total amount of dark energy increases, leading to an ever stronger repulsive force that drives the acceleration. The leading theoretical explanation for dark energy is the cosmological constant, which represents the energy of empty space itself, or vacuum energy. According to quantum mechanics, even a vacuum is not truly empty, but is filled with virtual particles constantly popping in and out of existence. These quantum fluctuations should contribute to the vacuum energy. However, theoretical calculations of this vacuum energy yield an astronomically large value, many orders of magnitude greater than what is observed for dark energy. This discrepancy, known as the cosmological constant problem, or the vacuum catastrophe, is one of the biggest unsolved puzzles in physics. It suggests that our understanding of vacuum energy is incomplete, or that there is some unknown mechanism that cancels out most of this energy, leaving only the tiny but significant amount we observe as dark energy. Alternative theories propose that dark energy is not a constant but a dynamic field, whose energy density can change over time. These models are broadly grouped under the term quintessence. Quintessence theories propose the existence of a new type of scalar field that permeates the universe similar to the Higgs field. The energy density of this field could evolve over cosmic time, potentially explaining why dark energy became dominant relatively recently in the universe's history. However, these models introduce additional complexity and require specific properties for this hypothetical field that are not yet confirmed by observations. Another set of theories attempts to explain the accelerating expansion, not by introducing a new energy component, but by modifying Einstein's theory of gravity itself on large cosmological scales. These modified gravity theories suggest that gravity behaves differently over vast distances or at very low curvatures of space-time, perhaps becoming repulsive at large scales. While intriguing, these models must be carefully constructed to remain consistent with all existing gravitational observations from the solar system to galaxy clusters. Dark energy's ultimate influence on the fate of the universe is profound. Its continued dominance will determine the long-term cosmic future. If dark energy remains a cosmological constant with a constant energy density, the universe will continue to expand at an accelerating rate indefinitely. This scenario, often referred to as the Big Freeze or heat death, would lead to a cold, empty, and extremely dilute universe. As space expands exponentially, distant galaxies would eventually recede from us faster than the speed of light, becoming causally disconnected and disappearing beyond our observable horizon. Eventually, even local galaxies might be gravitationally torn apart in an extreme version of this expansion, leaving behind a cold universe where stars eventually die out, and even black holes evaporate through Hawking radiation, leading to a state of maximum entropy. Other more speculative scenarios for the universe's fate depend on how dark energy might evolve. If dark energy's density were to increase over time, becoming even stronger and more repulsive, it could lead to a big rip. In this extreme scenario, the accelerating expansion would become so powerful that it would overcome even the forces holding atoms together, eventually ripping apart galaxies, stars, planets, and even atoms themselves. Conversely, if dark energy were to eventually dissipate or reverse its sign, it could potentially lead to a scenario where gravity eventually reasserts its dominance, causing the universe to stop expanding and eventually collapse back into a singularity, a big crunch resembling a reverse Big Bang. However, current observations strongly favour the cosmological constant scenario, suggesting a universe headed towards a big freeze. The existence of dark energy also poses a cosmic coincidence problem. Why is it that dark energy, which only became dominant relatively recently, is now of a comparable density to matter, just at the time when intelligent life has emerged to observe it? If dark energy had been dominant, much earlier structures like galaxies would not have formed. If it had only appeared much later, the universe would have spent a much longer time in a matter-dominated phase. This apparent coincidence might be a mere happenstance, or it could point to a deeper connection between the universe's properties and the emergence of observers, perhaps hinting at concepts like the anthropic principle, or a multiverse where our universe is one of many with different cosmological parameters. This problem is another key area of active research. The study of dark energy continues to be at the forefront of cosmological research. Future observatories and experiments such as the Nancy Grace Roman Space Telescope Euclid and the Vera C. Rubin Observatory are designed to make more precise measurements of dark energy's properties. By mapping the distribution of galaxies and supernovae across vast cosmic volumes, these missions aim to constrain whether dark energy is truly a constant, or if its properties change over time, potentially distinguishing between the cosmological constant and quintessence models, or even ruling out some modified gravity theories. Unravelling the nature of dark energy is perhaps the biggest puzzle facing modern physics, with profound implications for our understanding of gravity quantum mechanics and the ultimate destiny of the universe itself. The traditional understanding of the universe before the 20th century viewed space as a fixed three-dimensional stage and time as a separate universally flowing river. Events unfolded on this stage and time ticked by uniformly for everyone everywhere. This intuitive picture, deeply embedded in our everyday experience, formed the bedrock of Newtonian physics, which successfully described motion and gravity for centuries. However, this classical framework was fundamentally challenged and ultimately transformed by the revolutionary insights of Albert Einstein, particularly his theories of special and general relativity. These theories dramatically reshaped our understanding of space-time gravity and the very fabric of reality, demonstrating that space and time are not independent entities, but are intricately interwoven into a single, four-dimensional continuum known as space-time. This unified concept lays the essential groundwork for grappling with the profound question of the universe's origin and the nature of time itself. Einstein's journey began with the special theory of relativity published in 1905. This theory deals with the relationship between space and time for objects moving at constant velocities relative to each other in the absence of gravity. It is built upon two fundamental principles that Einstein took as given based on experimental evidence and logical consistency. The first postulate is the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion relative to one another. This means that if you are in a windowless room moving at a constant speed, you cannot perform any experiment to determine if you are moving or at rest. All physical laws, electricity, magnetism, mechanics, behave identically regardless of your constant velocity. This idea was not entirely new, as Galileo had hinted at it centuries before for mechanical laws. However, Einstein extended it to all laws of physics, including electromagnetism. The second and more revolutionary postulate is the principle of the constancy of the speed of light. This states that the speed of light in a vacuum, denoted by c, is the same for all observers regardless of their own motion or the motion of the light source. This was a radical departure from classical physics, where velocities simply added and subtracted. If you threw a ball forward on a moving train, the ball's speed relative to the ground would be its speed relative to the train plus the train's speed. But for light, this does not happen. Whether you are moving towards a light source or away from it at high speed or standing still, you will always measure the speed of light to be exactly approximately 300,000 kilometers per second. This seemingly simple postulate has profound and counterintuitive consequences for the nature of space and time. The implications of these two postulates are far-reaching and challenge our everyday notions of time and distance. One of the most famous consequences is time dilation. This phenomenon means that time passes more slowly for an object that is moving relative to an observer compared to an identical object that is at rest relative to the observer. Imagine two identical clocks, one on a fast-moving spaceship and one on Earth. An observer on Earth would see the clock on the spaceship ticking more slowly than the clock on Earth. Conversely, an observer on the spaceship would see the clock on Earth ticking more slowly. This is not just an illusion, but a real physical effect that has been experimentally verified countless times, for example, with atomic clocks on airplanes, or with subatomic particles called muons that are created in the Earth's atmosphere. Muons have a very short lifetime, but when they travel at speeds close to light, their lifetime appears to be extended from our perspective, allowing them to reach the Earth's surface before decaying. Time is not absolute, but relative to the observer's motion. Another startling consequence of special relativity is length contraction. This means that the length of an object measured by an observer is shorter in the direction of its motion relative to that observer compared to its length when it is at rest. If a spaceship is moving at a very high speed past Earth, an observer on Earth would measure the spaceship to be shorter in its direction of motion than its length would be if it were stationary. Again, the effect is mutual. An observer on the spaceship would measure Earth to be shorter in the direction of its motion. Like time dilation length contraction, is a real physical effect, although it only becomes noticeable at speeds approaching the speed of light. Special relativity also introduces the concept of relative simultaneity. Two events that appear to happen at the same time for one observer may not appear simultaneous for another observer who is in motion relative to the first. This means there is no universal now. The concept of past, present and future depends on the observer's frame of reference. This challenges the very notion of a single universal timeline. What is the past for one observer might still be the future for another, highlighting the interconnectedness and relativity of time and space. Perhaps the most famous outcome of special relativity is the equivalence of mass and energy encapsulated in the iconic equation E equals mc squared. This equation states that mass and energy E are interchangeable and are simply different forms of the same fundamental entity. A tiny amount of mass can be converted into an enormous amount of energy, because c squared is a very large number. This principle underlies nuclear processes such as those in atomic bombs and nuclear power plants. It implies that mass itself is a form of energy, and that changes in a system's energy will be accompanied by changes in its mass. This equation revolutionized physics, demonstrating that mass and energy are not conserved separately, but rather their combined total is conserved. The insights from special relativity hinted that space and time were not separate but intrinsically linked. This led Hermann Minkowski, Einstein's former mathematics professor, to formalize the concept of space-time. Minkowski realized that if time and space measurements were relative to an observer's motion, then they must be parts of a single, four-dimensional entity, a unified fabric. He famously declared, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics. Hereafter, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. In this four-dimensional space-time events are points, and the paths of objects through space-time are called world lines." While special relativity successfully described physics in the absence of gravity, it was Einstein's next great triumph, general relativity, that truly unveiled the profound nature of space-time. Einstein spent another decade grappling with the problem of incorporating gravity into his new relativistic framework. Newtonian gravity described gravity as a force that acted instantaneously across vast distances, a concept incompatible with the finite speed limit imposed by special relativity. Furthermore, Newton's theory did not explain how gravity actually worked. Einstein's breakthrough came with the realization that gravity is not a force in the traditional sense, but rather a manifestation of the curvature or warping of spacetime itself, caused by the presence of mass and energy. He published his general theory of relativity in 1915. The central idea of general relativity is captured by the equivalence principle, which states that gravity and acceleration are fundamentally indistinguishable. Imagine being in a windowless elevator. If the elevator is accelerating upwards in space, far from any gravitational source, you would feel pressed to the floor just as if you were standing in a gravitational field on Earth. Conversely, if the elevator cable broke and it was falling freely in a gravitational field, you would experience weightlessness just as if you were floating in space. This indistinguishability between acceleration and gravity led Einstein to his revolutionary insight that gravity is not a force pulling objects, but rather a consequence of the geometry of spacetime. In general relativity, spacetime is a dynamic and pliable fabric. Mass and energy cause this fabric to curve or warp. Think of a heavy bowling ball placed on a stretched rubber sheet. The bowling ball creates a dip in the sheet. If you then roll a marble across the sheet near the bowling ball, the marble will not move in a straight line, but will curve inwards towards the bowling ball, not because the bowling ball is pulling it with a force, but because the sheet itself is curved. Similarly, planets orbit the Sun, not because the Sun exerts a mystical force on them, but because the Sun's immense mass warps the spacetime around it, and the planets simply follow the shortest path, the geodesics, in this curved spacetime. The greater the mass or energy, the greater the curvature of spacetime. This explains gravity in terms of geometry rather than a force. General relativity made several groundbreaking predictions that have since been confirmed by observation and experiment. One of the earliest and most famous confirmations was the bending of light by gravity. Einstein predicted that light rays passing near a massive object like the Sun would be deflected from their straight path because the Sun's mass curves the spacetime around it. During a solar eclipse in 1919, British astronomer Arthur Eddington led an expedition that observed stars whose light passed close to the eclipsed sun. They found that the apparent positions of these stars were shifted precisely as predicted by Einstein's theory. This dramatic confirmation propelled Einstein to international fame and solidified general relativity's standing. Another key prediction is gravitational redshift. This refers to the phenomenon where light waves lose energy, and their wavelength stretches becoming redder as they climb out of a gravitational well. Conversely, light waves gain energy and become bluer as they fall into a gravitational well. This effect has been verified in laboratories using atomic clocks, and has also been observed with light from massive stars and galaxy clusters. For example, photons escaping from the strong gravitational field of a white dwarf star lose energy, and are therefore redshifted. Perhaps the most dramatic and relatively recent confirmation of general relativity is the detection of gravitational waves. These are ripples in the fabric of spacetime itself generated by extremely violent and energetic cosmic events, such as the collision of black holes or neutron stars. Einstein predicted the existence of these waves, but their direct detection proved incredibly challenging due to their tiny amplitude. After decades of technological development, the Laser Interferometer Gravitational Wave Observatory, or LIGO project, first directly detected gravitational waves in 2015, originating from the merger of two black holes. This monumental discovery opened up a whole new window for observing the universe, allowing us to study cosmic phenomena that do not emit light, providing further powerful confirmation of general relativity's accuracy. Other predictions include the precession of Mercury's orbit, which Newtonian gravity could not fully explain, and the existence of black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are extreme manifestations of space-time curvature, where mass is compressed into an incredibly small volume, creating a singularity at their core. The study of black holes and their properties is an active area of research, further testing the limits of general relativity. The profound implication of space-time as a unified four-dimensional fabric is particularly relevant when considering the origin of time. In the classical Newtonian view, time was an independent parameter that flowed uniformly regardless of anything else. But in relativity, time is intertwined with space and can be affected by motion and gravity. Time is not absolute. This means that if space-time itself has a beginning, as suggested by the Big Bang model, then time itself must have also had a beginning. It is not that the universe began in pre-existing time. Rather, time along with space and matter energy came into existence with the Big Bang. This conceptual shift is crucial. When we talk about before the Big Bang, it is not in the sense of a clock ticking prior to the universe's existence. If space-time itself began at the Big Bang singularity, then the concept of before loses its conventional temporal meaning. It is like asking what is north of the North Pole. The question assumes a direction that ceases to exist at that point. Similarly, asking what happened before time began assumes a temporal framework that may not have existed. This idea lays the fundamental groundwork for understanding the philosophical and scientific challenges of discussing the universe's ultimate origin, as it forces us to rethink our most basic assumptions about the nature of time itself. The concept of space-time fundamentally ties the question of the universe's beginning to the very origin of time. The understanding of space-time as a unified and dynamic entity is therefore not just an abstract mathematical construct, but a deeply physical reality confirmed by a century of experiments and observations. It is the stage upon which the cosmic drama unfolds, and its curvature is the very essence of gravity. This framework provides the essential conceptual tools to explore the universe's past, its current state, and its future fate. It prepares us for the mind-bending questions surrounding the Big Bang singularity and the potential emergence of time from a state that defies our everyday temporal intuition. The unified nature of space and time is a cornerstone of modern physics, and an indispensable guide to the mysteries of cosmic origins. The question of what existed before the Big Bang is one of the most profound and perplexing inquiries in cosmology and philosophy. Our everyday intuition dictates that every event must have a cause, and that there must always be a before for any given now. However, the standard Big Bang model, which describes the universe's evolution from an extremely hot, dense state, presents a radical challenge to this intuition. If space-time itself, the very fabric of space and time as we understand it, came into existence with the Big Bang, then the concept of before the Big Bang loses its conventional meaning. It is not merely a question of what was there, but rather whether the notion of a temporal there even applies. From a purely scientific perspective, the standard Big Bang model describes the universe's expansion from an initial singularity, a point of infinite density and temperature. At this singularity, the equations of general relativity which describe gravity and space-time break down. They do not tell us what happened at the singularity or what preceded it. This breakdown signifies a limit to our current physical theories. If space-time emerged from this singularity, then there was no time in the conventional sense for anything to exist before it. It's akin to asking what is south of the South Pole. The concept of south ceases to have geographical meaning beyond that point. Similarly, before might be a concept that applies only within the universe's timeline, not outside or prior to it. This scientific boundary immediately leads to philosophical challenges. Philosophers have grappled with the concept of nothingness and causality for millennia. The idea of something arising from literally nothing, the absence of even space and time, seems deeply counterintuitive. For many philosophical traditions, creation is often seen as the rearrangement of pre-existing material or an emanation from a divine source, rather than an absolute coming into being from absolute non-existence. The question, why is there something rather than nothing, posed by Leibniz encapsulates this deep philosophical unease. If there was truly absolute nothingness before the Big Bang, then what caused the Big Bang to happen? What could have prompted existence itself? If there was no time for a cause to precede its effect, what could the cause be if there was no space for it to exist? In these questions highlight the limits of applying our everyday notions of causality, which operate within a temporal framework, to the origin of that framework itself. Some philosophical arguments suggest that if time had a beginning, then the concept of before is meaningless, because it implies a prior state within a temporal sequence. If time itself did not exist, then there could be no prior state. This perspective suggests that the Big Bang is not an event in time, but rather the beginning of time. Therefore, asking what happened before the Big Bang is akin to asking what is outside the universe an illegitimate question, if the universe is defined as all of space-time. This argument shifts the focus from a temporal sequence to a question of fundamental existence and the nature of being. However, many scientists and philosophers find the idea of an absolute beginning of time and space uncomfortable. They explore various theoretical models that attempt to address the singularity and perhaps push the beginning to a different conceptual realm, or even eliminate it entirely. These models often rely on the principles of quantum mechanics, which governs the universe at its smallest scales and extreme energies. Our current understanding of general relativity is a classical theory of gravity, and it does not fully account for quantum effects at the singularity. A complete theory of quantum gravity is necessary to describe the very earliest moments of the universe. One approach is to consider time as an emergent property rather than a fundamental one. In some theoretical frameworks, time as we perceive it might not exist at the most fundamental level of reality, but instead emerges from a more primitive state. For instance, in certain quantum gravity models, space-time itself might be discretized, meaning it is not continuous, but made of tiny fundamental units. In such a scenario, the smooth flow of time might only become apparent at scales much larger than these fundamental units. At the Planck scale, the earliest conceivable moment time might be so different that our familiar notions of before and after simply do not apply. It could be that time as we know it crystallized or condensed out of a pre-geometric quantum foam, a state where space and time are not yet distinct. Several prominent theories of quantum gravity offer different perspectives on the Big Bang singularity and what might have preceded it. Loop quantum gravity, or LQG, is one such candidate theory. In LQG, space-time is not continuous, but is quantized into tiny discrete loops. This theory attempts to resolve the Big Bang singularity by suggesting that it is not a point of infinite density, but rather a quantum bounce. In this scenario, instead of collapsing to an infinitely dense point, the universe reached a minimum but finite size before rebounding into expansion. This implies that our universe could be the result of the collapse of a previous universe or a previous cosmological phase. If a quantum bounce occurred, then before our Big Bang would refer to the contracting phase of a prior universe. This removes the need for an absolute beginning for existence itself, although it shifts the question to what caused the first bounce or if there is an infinite series of bounces. String theory, another leading candidate for a theory of everything, also offers intriguing possibilities. String theory posits that fundamental particles are not point-like, but rather tiny vibrating strings. It also introduces the concept of extra spatial dimensions that might be curled up and hidden from our perception. In some string theory, inspired cosmological models, particularly those involving brains, our four-dimensional universe could be a brain or a membrane existing within a higher dimensional space called the bulk. The Big Bang in such models could be the result of a collision between two or more such brains. In a brain collision scenario before, the Big Bang would mean the state of these brains and the bulk space they inhabit before their collision. This implies a pre-existing reality, albeit one that is fundamentally different from our current universe. The collision itself would have released the enormous energy that created the matter energy and space-time we observe. The no-boundary proposal put forward by Stephen Hawking and James Hartle offers another fascinating way to think about the universe's origin. This proposal suggests that if we consider time as a complex number with both a real and an imaginary component, then at the beginning of the universe time behaved like space. In this imaginary time, the universe has no boundary, no beginning point in the conventional sense. It would be like the surface of a sphere which has no beginning or end but is finite. If one could trace the universe's history back using imaginary time, they would not encounter a singularity or a sharp beginning point. While complex and mathematically abstract, this proposal suggests that the question, what was before the Big Bang, is akin to asking, what is north of the North Pole? It is a question that simply does not apply in that specific mathematical framework. In essence, it implies that the universe spontaneously came into existence without needing a before or a cause in the traditional sense because it had no initial boundary. Cyclic universe models also attempt to address the before Big Bang question by proposing an eternal cycle of expansion and contraction or bounces. In these models, the Big Bang is not the ultimate beginning, but simply a transition point in an ongoing cosmic cycle. Our universe might expand for billions of years, eventually contracting back into a big crunch, or perhaps avoiding a singularity through a big bounce, only to re-expand into a new Big Bang. In such scenarios, before, our Big Bang simply refers to the contracting or previous phase of the cosmos. Examples include the oscillating universe model where gravity eventually pulls everything back together, and the ekpyrotic cyclic model where the collision of brains repeatedly triggers new Big Bangs. These models resolve the before question by suggesting that something always existed in some form, albeit a constantly changing one. The idea of a multiverse also impacts the concept of before time. If our universe is just one of an infinite number of universes, each potentially with its own Big Bang, then before our Big Bang could refer to the meta-space or underlying framework from which these multiple universes originated. For instance, in eternal inflation theory, inflation never truly ends in all regions of space, instead continuously creating new pocket universes. In this view, our Big Bang is just one bubble universe inflating out of an ever-inflating background space. In such a scenario, the question of before our Big Bang expands to the question of what existed before the meta-universe itself. This pushes the problem to a higher level but does not eliminate it. These various theoretical models, from quantum gravity to multiverse scenarios, all try to address the fundamental problem posed by the Big Bang singularity. They attempt to describe a state from which our universe emerged without necessarily invoking a conventional before. Some suggest that time itself is an emergent property only becoming meaningful after a certain point in cosmic evolution. Others propose that what we perceive as the Big Bang is merely a phase transition or a bounce from a pre-existing state, whether it be a previous universe, higher dimensions, or a quantum foam. The core challenge is that our human experience of time is inherently linear and unidirectional, making it incredibly difficult to conceptualize a reality where time itself has a beginning or where our conventional notions of past, present, and future simply do not apply. The absence of a definitive answer to what was before the Big Bang is a testament to the limits of our current scientific knowledge and the profound nature of reality itself. It forces us to confront the boundaries of our understanding and the limitations of our language and concepts when applied to the very origin of existence. While scientific progress continues to push back the frontiers of our knowledge, the ultimate question of why there is something rather than nothing, and what truly lies beyond or before our cosmos may remain a profound mystery, bridging the realms of science, philosophy, and pure speculation. The conceptual groundwork provided by general relativity and the concept of space-time is essential for even formulating these questions in a coherent manner, as it tells us that time itself is part of the reality that had a beginning. Therefore, the before becomes a deeply nuanced and challenging concept rather than a simple temporal predecessor. The world we experience every day operates according to rules that seem entirely logical and intuitive. Objects have definite positions and speeds. Events unfold in a predictable sequence of cause and effect. This classical view of reality, enshrined by Isaac Newton's laws of motion and gravity, served as the bedrock of scientific understanding for centuries. However, as the 20th century dawned, scientists began to probe the universe at its most fundamental scales, exploring the behavior of atoms and their constituents. What they discovered was profoundly unsettling and utterly counterintuitive. The laws governing the very small, the realm of particles and waves, were radically different from the classical rules of the macroscopic world. This new understanding became known as quantum mechanics, a theory that revolutionized physics and forced us to rethink the very nature of reality. Its principles are essential for understanding the extreme conditions of the very early universe and form the basis of quantum cosmology. The genesis of quantum mechanics can be traced to several perplexing phenomena that classical physics simply could not explain. One such puzzle was black body radiation, the way objects emit light when heated. Classical theory predicted that a hot object should emit an infinite amount of ultraviolet light, a phenomenon dubbed the ultraviolet catastrophe, which was clearly not observed in reality. In 1900, Max Planck provided a revolutionary solution. He proposed that energy is not continuous, but is emitted and absorbed in discrete packets or bundles, which he called quanta. The energy of each quantum was directly proportional to the frequency of the radiation, with the proportionality constant now known as Planck's constant, a fundamental value in quantum mechanics. This groundbreaking idea marked the birth of quantum theory, although Planck himself initially viewed it more as a mathematical trick than a fundamental aspect of reality. Another mystery was the photoelectric effect, where light shining on a metal surface can eject electrons. Classical wave theory of light predicted that the energy of the emitted electrons should depend on the intensity of the light, and that any frequency of light could eventually eject electrons if the intensity was high enough. However, experiments showed that electron ejection only occurred if the light's frequency exceeded a certain threshold, regardless of its intensity, and that the energy of the emitted electrons depended on the light's frequency, not its intensity. In 1905, Albert Einstein, building on Planck's idea, proposed that light itself consists of discrete packets of energy, called photons. Each photon has an energy proportional to its frequency. For an electron to be ejected, it must absorb a single photon, with enough energy to overcome the binding forces in the metal. If the photon's energy is below the threshold, nothing happens no matter how many photons hit the surface. This concept of light behaving as particles further solidified the idea of quantization. Perhaps the most famous and unsettling feature of quantum mechanics is wave-particle duality. This concept states that entities like electrons, protons, and even light itself do not behave exclusively as either particles or waves, but can exhibit characteristics of both, depending on how they are observed or interacted with. Light, traditionally considered a wave phenomenon, was shown by Einstein's work on the photoelectric effect to behave like particles' photons. Conversely, particles like electrons, which were classically thought of as tiny billiard balls, were shown by experiments like the double-slit experiment to exhibit wave-like behavior. The double-slit experiment is a powerful demonstration of wave-particle duality. If you fire electrons one by one at a barrier with two narrow slits behind it, and then observe where they land on a screen, you would expect to see two distinct bands corresponding to electrons passing through one slit or the other, like tiny bullets. However, what is observed is an interference pattern, a series of alternating bright and dark bands characteristic of waves interfering with each other. This suggests that each individual electron somehow passes through both slits, simultaneously behaving like a wave. But if you then try to detect which slit the electron goes through, the interference pattern disappears and you get two distinct bands. The act of observation seems to force the electron to choose a definite path, confirming its particle nature. This profound result highlights that the quantum world is fundamentally different from our macroscopic experience, where objects always have a definite location and follow a definite path. A cornerstone of quantum mechanics is the concept of superposition. This principle states that a quantum system, such as an electron or an atom, can exist in multiple possible states simultaneously until it is measured or observed. It is as if the particle exists in all its potential states at once, a probabilistic cloud of possibilities, rather than a single definite state. Only upon measurement does the system collapse into one particular definite state. The famous thought experiment of Schrödinger's cat illustrates this idea. Imagine a cat in a sealed box with a vial of poison connected to a device that will release the poison if a single radioactive atom decays. According to quantum mechanics, until the box is opened and the atom's state is observed, the atom exists in a superposition of decayed and undecayed states. This implies that the cat itself is in a superposition of being both alive and dead simultaneously, until the act of observation forces it into one definite state. While this is a thought experiment designed to highlight the strangeness of quantum mechanics, it vividly illustrates the counterintuitive nature of superposition. Related to superposition is the probabilistic nature of quantum mechanics. Unlike classical physics, where if you know the initial conditions of a system you can predict its future state, with certainty quantum mechanics only allows us to predict the probabilities of various outcomes. We cannot say for sure where a particular electron will be at a given time or which energy state an atom will occupy. Instead, we can calculate the probability of finding it at a certain location or in a particular state. This inherent randomness is not due to our lack of knowledge or limitations in our measuring instruments. It is a fundamental and irreducible aspect of quantum reality. The mathematical framework of quantum mechanics uses wave functions to describe the state of a particle or system. The square of the amplitude of the wave function at any point gives the probability of finding the particle at that point. This probabilistic interpretation, known as the Born rule, is central to making predictions in quantum mechanics. Perhaps the most famous principle that sets quantum mechanics apart from classical physics is Werner Heisenberg's uncertainty principle, formulated in 1927. This principle states that it is impossible to simultaneously know with perfect precision certain pairs of complementary properties of a particle. The most common example is position and momentum. If you precisely measure the position of a particle, you necessarily introduce uncertainty into its momentum and vice versa. Similarly, there is an uncertainty relationship between energy and time. The more precisely you measure the energy of a system, the less precisely you can know the time for which it had that energy and vice versa. This is not a limitation of our measuring devices, but a fundamental property of nature itself. It implies that at the quantum level, reality is inherently fuzzy and indeterminate. We cannot simultaneously pinpoint every property of a particle as we might a classical object. The act of measurement in quantum mechanics is a complex and still debated topic, known as the measurement problem. When a quantum system in a superposition of states is measured, it appears to instantaneously collapse into one of those definite states. What precisely constitutes a measurement, and how this collapse occurs, is a deep conceptual challenge. Does consciousness play a role? Does interaction with a classical measuring apparatus cause the collapse? Various interpretations of quantum mechanics, such as the Copenhagen interpretation, the many worlds interpretation and others, offer different ways to understand this phenomenon, but none have achieved universal consensus. Regardless of the interpretation, the practical consequence is that the outcome of a quantum measurement is inherently probabilistic. Quantum mechanics also introduced the concept of quantum entanglement. When two or more particles become entangled, their fates are linked in such a way that they share a single quantum state. Measuring a property of one entangled particle instantaneously determines the corresponding property of the other particle, no matter how far apart they are. This seems to violate the classical notion that information cannot travel faster than light, but it does not allow for faster than light communication. Entanglement highlights the non-local nature of quantum reality, where particles can be intimately connected across vast distances. The principles of quantum mechanics extend beyond individual particles to quantum fields. In modern quantum field theory, every fundamental particle is understood as an excitation or a vibration of an underlying quantum field that permeates all of space. For example, there is an electron field, a photon field, a quark field, and so on. Particles are not distinct little balls, but rather localized excitations of these fields. The quantum vacuum, the lowest energy state of these fields, is not empty, but is filled with the potential for particles to emerge from it. This concept of quantum fields is crucial for understanding phenomena like vacuum fluctuations. The implications of quantum mechanics are profound for our understanding of the universe, especially its earliest moments. Classical physics and Einstein's general relativity, which describes gravity at large scales, predict a singularity at the beginning of the Big Bang, a point of infinite density and temperature where space-time breaks down. However, at such extreme conditions where matter and energy are compressed to unimaginably small scales, quantum effects would dominate. General relativity, a classical theory, is simply inadequate to describe the universe at the Planck epoch, the first 10 to the power of minus 43 seconds. A theory of quantum gravity which would unify general relativity with quantum mechanics is needed to fully understand what happened at or before the Big Bang singularity. Concepts like superposition uncertainty in quantum fields are fundamental to quantum cosmology, which attempts to apply quantum mechanics to the entire universe. For instance, theories about the universe spontaneously appearing from a quantum vacuum, or the idea of the universe existing in a superposition of different possible states before measurements of the cosmic microwave background narrowed down its properties, all rely heavily on quantum principles. The inherent probabilistic nature of quantum mechanics also suggests that the initial conditions of the universe might not have been uniquely determined, but rather emerged from a range of possibilities. Understanding this quantum reality with its wave-particle duality, superposition, uncertainty, and probabilistic outcomes is therefore an essential prerequisite for exploring the most speculative and fundamental questions about the universe's origin and its earliest evolution. It opens up a universe that is far stranger, more dynamic, and less deterministic than our everyday experience suggests. When we think of empty space, we often imagine a void where nothing exists, a vast expanse devoid of matter, energy, or even light. In classical physics, a vacuum is precisely that, the absence of all particles and fields. However, the profound insights of quantum mechanics paint a radically different picture of emptiness. In the quantum realm, a vacuum is far from inert and lifeless. Instead, it is a vibrant, bubbling sea of activity teeming with what are known as vacuum fluctuations, where particles momentarily pop into and out of existence. This concept of the quantum vacuum being a dynamic entity, rather than absolute nothingness, has profound implications for our understanding of reality, and particularly for speculative theories about the universe's origin. The fundamental reason for this ceaseless activity in the quantum vacuum lies in Werner Heisenberg's uncertainty principle, specifically the energy-time uncertainty relation. This principle states that you cannot simultaneously know with perfect precision both the energy of a system and the time for which it possessed that energy. There is an inherent fuzziness in nature that prevents such absolute certainty. This means that for very short periods of time there can be a temporary violation of energy conservation. Energy can be borrowed from the vacuum for a brief moment as long as it is paid back within a time frame allowed by the uncertainty principle. The more energy borrowed, the shorter the time it can exist. This is the mechanism that allows for the spontaneous appearance and disappearance of virtual particles from the vacuum. These ephemeral particles that wink into and out of existence are called virtual particles. They are not real in the sense of stable, propagating particles that can be directly observed or detected over long periods. Instead, they are transient excitations of quantum fields. According to quantum field theory, every fundamental particle in the universe, electrons, quarks, Photons is an excitation or a ripple in an underlying quantum field that permeates all of space. The vacuum state is simply the lowest energy state of all these quantum fields, a state where there are no observable stable particles. However, even in this lowest energy state, the fields themselves are always fluctuating. These fluctuations are the virtual particles. Virtual particles almost always appear in particle-antiparticle pairs. For instance, an electron and its antiparticle, a positron, might spontaneously emerge from the vacuum, exist for an incredibly short time, and then annihilate each other, converting their combined mass back into energy or photons. Similarly, quark-antiquark pairs or virtual photons can emerge. These interactions are so rapid that they cannot be directly observed, but their effects are measurable and have been experimentally verified. One of the most striking pieces of experimental evidence for the reality of vacuum fluctuations is the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that if two uncharged parallel metallic plates are placed extremely close together in a vacuum, they will experience a tiny but measurable attractive force pulling them towards each other. This counterintuitive force arises because the space between the plates restricts the possible wavelengths of virtual photons that can exist there. Only virtual photons with wavelengths that fit neatly between the plates can exist in the gap. Outside the plates, however, there are no such restrictions, so a wider range of virtual photon wavelengths is possible. This difference in the allowed quantum fluctuations creates a net force. The pressure exerted by the virtual photons outside the plates is greater than the pressure exerted by the virtual photons inside the plates, resulting in an attractive force pushing the plates together. The Casimir effect has been precisely measured in laboratory experiments, providing compelling evidence for the physical reality of vacuum fluctuations and the inherent energy of the quantum vacuum. Another crucial piece of evidence comes from the Lamb shift observed in the hydrogen atom. In classical electrodynamics and even early quantum models, the 2s and 2p energy levels of the hydrogen atom were predicted to have exactly the same energy. However, in 1947, Willis Lamb and Robert Rutherford discovered a tiny but definite shift in the energy of the 2s level relative to the 2p level. This small energy difference could not be explained by existing theories. It was later explained by quantum electrodynamics QED, which showed that the electron in the hydrogen atom constantly interacts with virtual photons that pop into and out of existence in the surrounding quantum vacuum. These interactions slightly shift the electron's energy levels, causing the Lamb shift. This phenomenon provides direct evidence that the quantum vacuum is not empty, but is filled with a dynamic sea of virtual particles constantly interacting with real particles. Spontaneous emission is yet another phenomenon explained by vacuum fluctuations. If an atom is in an excited energy state, classical physics predicts that it should remain in that state indefinitely, unless it is perturbed by an external electromagnetic field. However, atoms in excited states spontaneously emit photons and decay to lower energy states, even in what appears to be empty space. This process is initiated by the interaction of the atom's electrons with the fluctuating electromagnetic field of the quantum vacuum. The virtual photons in the vacuum stimulate the excited electron to drop to a lower energy level, releasing a real photon. This constant interaction with the quantum vacuum prevents atoms from remaining in excited states forever, and explains the natural decay of excited atoms. The concept of the quantum vacuum being filled with activity fundamentally changes our understanding of nothing. In classical terms, nothing means absolute emptiness. In quantum terms, empty space is never truly empty. It is the lowest possible energy state of the universe, but it is inherently dynamic and contains latent energy and potential. This lowest energy state is often referred to as the 0-point energy, because it represents the minimum energy present even at absolute zero temperature when all classical motion ceases. The existence of this 0-point energy implies that even in the absence of observable matter or radiation, the quantum vacuum possesses an intrinsic energy density. This concept has profound implications for cosmology, particularly in the context of the universe's origin. The idea that the universe could have emerged from nothing is recontextualized by the quantum vacuum. If nothing is interpreted as the quantum vacuum rather than an absolute philosophical void, then the universe is not necessarily created from absolute non-existence. Instead, it could have emerged from a highly energetic and dynamic quantum state that has inherent properties and the potential for existence. This is a crucial distinction. The universe originating from a quantum vacuum is not the same as it originating from a state of literally no being whatsoever. The quantum vacuum is not nothing, but a fundamental something that is constantly bubbling with virtual particles and fluctuations. This understanding is central to some speculative theories about the universe's origin. One such idea is that the Big Bang itself could have been a gigantic quantum fluctuation in a pre-existing quantum vacuum. In this scenario, a tiny quantum fluctuation in the vacuum could have grown unstable and expanded rapidly due to a process like inflation giving rise to the entire universe we observe. This doesn't mean the universe appeared from absolute void, but from a pre-existing quantum substratum or a meta-vacuum, which itself is far from empty. Such a quantum fluctuation would not violate energy conservation in the long term, because the total energy of the universe is thought to be zero, or very close to zero, with the positive energy of matter and radiation being balanced by the negative gravitational potential energy. Furthermore, quantum fluctuations are believed to have played a crucial role in providing the initial seeds for structure formation in the universe. The theory of cosmic inflation proposes a period of extremely rapid expansion in the very early universe. During this inflationary epoch, tiny quantum fluctuations that existed at subatomic scales were stretched to macroscopic cosmological scales. These stretched quantum fluctuations became the primordial density variations, or inhomogeneities, in the early universe, which are observed as the faint temperature anisotropies in the cosmic microwave background radiation. These tiny overdense and underdense regions then grew through gravity over billions of years, forming the large-scale structures like galaxies and galaxy clusters we see today. So the very fabric of the cosmic web, the distribution of matter in the universe, originated from the fundamental fuzziness and activity of the quantum vacuum during inflation. The concept of a false vacuum is also relevant in this context. In some inflationary models, the early universe is thought to have existed in a false vacuum state. This false vacuum is a quantum state that is not the lowest possible energy state, but is stable for a period. It possesses a very high energy density similar to a cosmological constant. When this false vacuum eventually became unstable, it decayed or tunneled to a lower energy state, a true vacuum, releasing its enormous energy and triggering the Big Bang expansion and the creation of matter and radiation. In this view, the universe did not appear from absolute nothingness, but from the decay of a high-energy quantum vacuum state that existed prior to the hot Big Bang. The Hawking-Hartle no-boundary proposal also touches upon the quantum nature of the universe's origin. While highly mathematical, this proposal suggests that the universe did not have a definite beginning in the traditional sense, but rather spontaneously arose from a quantum state without a boundary or a singularity. It is a quantum mechanical description of the universe's origin, where the very concept of space-time emerges from a quantum foam without needing an initial temporal before. This implies a universe that essentially creates itself from quantum laws without external intervention or a pre-existing time. The implications of vacuum fluctuations and the quantum nature of the vacuum are profound for cosmology. They suggest that the nothing before the Big Bang was not an absolute void, but a highly energetic and dynamic quantum state with inherent properties and the potential for existence. This shifts the fundamental question from how did something come from literally nothing to how did our specific universe emerge from the complexities of the quantum vacuum. It implies that the universe's origin might be governed by the same quantum laws that dictate the behavior of particles at the subatomic level, continuously pushing the boundaries of our understanding of existence itself. The quantum vacuum, far from being empty, is a vibrant foundation for reality. Modern physics rests on two towering pillars of understanding, each remarkably successful in its own domain but fundamentally incompatible with each other. On one side stands Albert Einstein's general theory of relativity, which describes gravity as the curvature of space-time and governs the universe on large cosmological scales, from stars and galaxies to the very expansion of the cosmos. On the other side is quantum mechanics, the theory that describes the behavior of matter and energy at the smallest subatomic scales, dictating the world of particles and forces like electromagnetism and the nuclear forces. Both theories have been extensively verified by countless experiments and observations, but they employ entirely different conceptual frameworks and mathematical languages. The quest for quantum gravity is the ambitious endeavour to reconcile these two fundamental theories into a single coherent framework, a theory that can describe the entire universe from its largest structures to its smallest constituents and unravel the mysteries of its ultimate origin. General Relativity, which Einstein published in 1915, revolutionized our understanding of gravity. It abandoned the Newtonian idea of gravity as an instantaneous force acting between masses and replaced it with a geometric description. In General Relativity, mass and energy warp the fabric of space-time, and what we perceive as gravity is simply objects following the shortest paths in this curved space-time. The theory has been spectacularly successful in explaining a wide range of phenomena. It accurately predicts the precise orbits of planets, including the subtle precession of Mercury's orbit, which Newtonian gravity could not fully account for. It predicted the bending of light by massive objects, a phenomenon famously confirmed during a solar eclipse. General Relativity also predicted the existence of black holes regions of space-time, where gravity is so strong that nothing, not even light, can escape. Its most recent triumph was the direct detection of gravitational waves ripples in space-time itself, caused by catastrophic cosmic events like the collision of black holes a century after Einstein first predicted them. General Relativity is a classical theory, meaning it describes phenomena in a continuous deterministic way, without involving the probabilistic and quantized nature of the quantum world. Its domain is the macroscopic universe, where gravity is the dominant force. In stark contrast, quantum mechanics, which developed concurrently with general relativity in the early 20th century, focuses on the microscopic world of atoms and subatomic particles. It introduced revolutionary and often counterintuitive concepts such as wave-particle duality, where particles can behave like waves, and vice versa, superposition, where a particle can exist in multiple states simultaneously until measured, and the uncertainty principle, which states that certain pairs of properties like position and momentum cannot be known with perfect precision at the same time. Quantum mechanics is fundamentally probabilistic. It predicts the likelihood of certain outcomes rather than definite results. This theory has been incredibly successful in explaining the behavior of atoms, the emission of light, the structure of materials, and the interactions of elementary particles. The standard model of particle physics, which describes the electromagnetic weak and strong nuclear forces and all known elementary particles except for the graviton, is a highly successful quantum field theory built upon the principles of quantum mechanics. Its predictions have been confirmed with astonishing precision in particle accelerators around the world. The fundamental incompatibility between general relativity and quantum mechanics arises from their differing descriptions of reality. General relativity treats space-time as a smooth, continuous and flexible fabric that can be curved and warped by mass and energy. Quantum mechanics, on the other hand, describes energy and matter in discrete quantized packets. When physicists attempt to apply the quantization procedures of quantum mechanics to the gravitational field, which is what general relativity describes, they run into insurmountable mathematical difficulties leading to infinities that cannot be removed in a consistent way. The gravitational force is incredibly weak at the scales where quantum effects become dominant, far weaker than the electromagnetic or nuclear forces. This weakness makes it extremely difficult to observe quantum gravitational effects directly. While photons mediate the electromagnetic force, and gluons mediate the strong force, the hypothetical particle that would mediate the gravitational force is called the graviton. However, a quantum theory of gravity that successfully incorporates gravitons and their interactions with other particles remains elusive. The quest for quantum gravity is not merely an academic exercise. It is absolutely necessary to resolve some of the most profound outstanding mysteries in physics and cosmology. One of the most compelling reasons is the Big Bang singularity. General relativity predicts that the universe began from a point of infinite density and temperature, where space-time curvature becomes infinite. At this singularity, the equations of general relativity break down completely, and our current laws of physics cease to apply. They cannot describe what happened at the Big Bang, or what, if anything, existed before it. A theory of quantum gravity is essential to understand this initial moment, perhaps resolving the singularity and providing a coherent description of the very early universe where all matter and energy were compressed into an unimaginably tiny volume, and quantum effects of gravity would have been dominant. Such a theory might reveal that the Big Bang was not an absolute beginning, but a transition from a prior state, perhaps a quantum bounce from a contracting universe, or an emergence from a state where space and time as we know them did not yet exist. Similarly, quantum gravity is needed to understand the singularities predicted inside black holes. General relativity predicts that at the heart of a black hole, matter collapses to an infinitely dense point, a singularity where again, its equations fail. A theory of quantum gravity is required to describe the physics inside black holes at these extreme conditions, and to address fundamental puzzles like the black hole information paradox, which questions whether information about matter falling into a black hole is permanently lost, or if it is somehow preserved. A quantum theory of gravity might reveal that black hole singularities are also resolved, perhaps replaced by a finite dense region, or a wormhole connecting to another part of space-time. Beyond these singularities, the quest for quantum gravity is driven by the grand vision of unifying all fundamental forces of nature. The standard model of particle physics successfully describes the strong, weak and electromagnetic forces, but it excludes gravity. Physicists dream of a theory of everything, a single, elegant framework that can describe all forces and particles in the universe as different manifestations of a single underlying reality. Such a theory would provide a deeper and more complete understanding of how the universe works, and might also offer explanations for the precise values of fundamental physical constants, which currently appear arbitrary. It would be the ultimate intellectual triumph, unifying all of physics under one coherent roof. Another fundamental reason for quantum gravity lies in the very nature of space-time itself. If energy and matter are quantized as quantum mechanics tells us, then it seems logical that the fabric of space-time, which is warped by energy and matter, should also exhibit quantum properties. At incredibly small scales, known as the Planck scale, space-time might not be smooth and continuous as in general relativity, but rather lumpy, foamy or granular. It might consist of discrete units or quanta of space and time themselves. The Planck length, approximately 10 to the power of minus 35 meters, is the scale at which quantum gravitational effects are expected to become significant. Below this scale, our familiar notions of continuous space and time may break down entirely. A theory of quantum gravity would provide insights into the microstructure of space-time at these extreme scales. Developing a theory of quantum gravity is arguably the biggest challenge in modern theoretical physics. One of the primary difficulties is the complete lack of experimental data from the quantum gravity regime. The Planck scale is unimaginably small, and the energies required to probe such scales are astronomically high, far beyond the capabilities of any conceivable particle accelerator on Earth. This means that physicists do not have empirical guideposts to test and refine their theoretical models directly. They must rely heavily on mathematical consistency, logical coherence, and the ability of a theory to unify existing knowledge and make predictions that might one day be testable, even if indirectly. The extreme mathematical complexity involved in trying to combine the intricacies of general relativity with the probabilistic nature of quantum mechanics also poses a formidable barrier. Despite these immense challenges, several ambitious theoretical approaches are being pursued to formulate a theory of quantum gravity. The two most prominent contenders are string theory and loop quantum gravity, which will be discussed in more detail in subsequent sections. Other approaches include causal dynamical triangulations, which build space-time from fundamental geometric building blocks, non-commutative geometry, which explores the idea that space-time might not be described by ordinary coordinates, and various types of quantum cosmology models that apply quantum principles directly to the entire universe. Each approach has its own strengths, weaknesses, and unique conceptual framework for thinking about the fundamental nature of reality. The search for quantum gravity is not just about combining two theories, it is about pushing the boundaries of human understanding into realms where our everyday intuition about space-time and causality breaks down. It is a quest for the ultimate laws that govern the universe's origin and its most fundamental structure, a pursuit driven by the enduring human desire to understand the entirety of existence. Among the leading contenders in the quest for a theory of quantum gravity loop, Quantum gravity, or LQG, stands out as a distinct and compelling approach, while other theories like string theory aim to unify all fundamental forces including gravity by proposing a new fundamental constituent of matter and energy. LQG focuses specifically on quantizing spacetime itself. Its core philosophy is to apply the principles of quantum mechanics directly to Einstein's general theory of relativity in a rigorous and non-perturbative way, leading to a granular or atomic picture of space and time at the smallest scales. It offers a powerful framework for addressing the Big Bang singularity and the nature of space and time at the universe's origin. The foundational principles of loop quantum gravity begin with a reformulation of general relativity. Instead of working directly with spacetime as a smooth, continuous manifold, LQG re-expresses Einstein's equations using a mathematical language that is more amenable to quantum treatment. This involves transforming the gravitational field into a set of variables known as Ashtekar variables, which resemble the electric and magnetic fields used in electromagnetism. This reformulation allows the gravitational field to be treated in a way that is more analogous to how other forces are handled in quantum field theory, making it easier to apply standard quantization procedures. A key aspect of this approach is its background independence. Unlike some other quantum gravity theories, LQG does not assume the existence of a fixed pre-existing spacetime background. Instead, spacetime itself emerges as a dynamic and quantum entity, consistent with the spirit of general relativity, where spacetime is not merely a stage, but an active participant shaped by matter and energy. One of the most profound and central predictions of loop quantum gravity is the quantization of space itself. In classical physics, space is assumed to be infinitely divisible. You can always imagine dividing a length into smaller and smaller parts without limit. However, in LQG, this is not the case. The theory predicts that space is not continuous, but rather composed of tiny, discrete, irreducible units, or atoms of space. These fundamental units are extremely small, on the order of the Planck length approximately 10 to the power of minus 35 meters, below which space cannot be further subdivided. This means that area and volume also come in discrete quantized packets. There is a minimum possible area and a minimum possible volume that can exist in the universe. It is akin to pixels on a digital image, or atoms making up a substance. From this perspective, space is not a smooth backdrop but a network of interconnected quantum excitations. The mathematical structures that represent these quantized units of space in LQG are called spin networks. A spin network is a graph-like structure where the lines represent fundamental loops, or edges, of excited gravitational field, and the nodes where these lines meet represent fundamental units of volume. Each edge and node carries a quantum number, a spin quantum number, that specifies the quantized area and volume respectively. These spin networks evolve over time to form structures called spin foams, which represent the quantized fabric of spacetime evolving from one moment to the next. The geometry of spacetime at the Planck scale is described not by a smooth manifold, but by these discrete quantum graphs. The resolution of the Big Bang singularity is one of the most significant triumphs claimed by loop quantum gravity. In general relativity, the Big Bang is predicted to be a point of infinite density and infinite spacetime curvature, where our current laws of physics break down. LQG, however, provides a mechanism to avoid this singularity. According to LQG, as the universe contracts and its density increases, the quantum nature of spacetime becomes dominant. Instead of collapsing to an infinitely dense point, the universe reaches a state of maximum but finite density and curvature. At this point, the repulsive effects of quantum gravity become so strong that they overcome the attractive force of classical gravity, causing the universe to bounce and re-expand. This is known as the quantum bounce, or big bounce, rather than a big bang from nothing. This quantum bounce implies that our universe did not necessarily originate from an absolute beginning of nothingness, but could have emerged from the collapse of a previous universe or a prior cosmological phase. In this view, the universe has undergone an eternal cycle of contraction and expansion, with a bounce replacing the singularity. This scenario provides a continuous cosmological evolution, avoiding the conceptual difficulties of a true beginning of time and existence from an infinitely dense point. The quantum bounce mechanism also offers a potential solution to the information paradox in black holes, suggesting that the singularity inside a black hole is also resolved with matter either rebounding or passing through to another region of space-time rather than being lost forever. The nature of time itself is also profoundly reinterpreted in loop quantum gravity. In LQG, time is not an external parameter or a universal clock that ticks independently of the universe. Instead, time is seen as an emergent property arising from the dynamics of the spin network. It is defined by the changes and evolutions within the fundamental quantum geometric structures. This approach helps to address the problem of time in quantum gravity, which arises when attempting to quantize a theory like general relativity, where time is treated as a coordinate that can be dynamically warped. In LQG, time becomes relational, meaning it is defined by the relationships between the various components of the universe, rather than being an absolute background against which events unfold. This concept implies that at the very fundamental scales of space-time where the quantum bounce occurs, the familiar notion of a smoothly flowing continuous time may not apply. A significant challenge and also a defining characteristic of loop quantum gravity is its relationship with other fundamental forces and the standard model of particle physics. LQG is primarily a theory of quantum gravity. It aims to quantize space-time and gravity directly, but it does not inherently include the other fundamental forces like electromagnetism, or the strong and weak nuclear forces, or the particles described by the standard model. This means that LQG is not a theory of everything, in the same sense that string theory often claims to be. While efforts are underway to incorporate matter and gauge fields into the LQG framework, this remains a complex and ongoing area of research. The hope is that a unified picture would eventually emerge, perhaps with the other forces and particles being built upon the quantum geometric structure provided by LQG. The mathematical framework of loop quantum gravity is highly sophisticated, involving concepts from differential geometry and quantum field theory. It utilizes a canonical quantization approach where the gravitational field is broken down into its fundamental components and then quantized. Key mathematical objects in LQG include holonomies, which measure the curvature of spacetime along loops, and fluxes, which measure the area of surfaces. These mathematical constructs are what ultimately give rise to the discrete nature of space and the spin network formalism. Loop quantum gravity boasts several strengths. Its background independence is a major advantage, aligning with the spirit of general relativity. It is a non-perturbative theory, meaning it does not rely on approximations that break down at high energies, unlike earlier attempts to quantize gravity. Most importantly, it offers a concrete mechanism to resolve the Big Bang and black hole singularities, replacing them with finite curvature events like the quantum bounce. It also makes specific predictions such as the quantization of area and volume, which are testable in principle even if currently beyond our technological reach. However, LQG also faces significant challenges. The most critical challenge is the lack of experimental verification. The predictions of LQG, such as the discrete nature of space and time, occur at the Planck scale energies far beyond our current experimental capabilities. Indirect tests are being explored, for instance, searching for tiny deviations from light speed or effects on cosmic ray propagation that might be caused by a granular spacetime, but definitive evidence remains elusive. Another conceptual challenge is the recovery of classical general relativity at macroscopic scales. While LQG aims to be a full quantum theory of gravity, demonstrating how it smoothly transitions to the familiar continuous spacetime of Einstein's theory, at large scales is a complex task. The incorporation of matter and other forces, as mentioned, remains an ongoing area of research. Despite these challenges, loop quantum gravity remains a powerful and intriguing candidate for a theory of quantum gravity, providing a unique perspective on the fundamental nature of spacetime and the origin of our universe.